Imagine a box, a perfect container, sealed off from everything we know. Inside, we have tried to create the purest form of nothing possible. There is no air, no light, no stray particles of heat or radiation. It is, in theory, the embodiment of emptiness. And yet, if this box could be built and placed on a scale, it would have weight. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This idea feels wrong. It seems to contradict a simple, fundamental logic. Nothing is the absence of something. The absence of something should weigh nothing at all. This intuition feels solid, unshakable. But in physics, as in deep time, what feels normal is not always the whole story. The laws that govern our universe suggest that our intuition is incomplete. And by the end of this journey, we will have uncovered one of the strangest truths about our reality: how the void itself can tip the scales. This is not a riddle. It is a question that leads to the very edge of our understanding of space and energy. To begin, we have to set aside our everyday definition of nothing. In the world of physics, true, absolute emptiness simply does not exist. The universe, it turns out, is never truly quiet. It cannot be. And that simple, disruptive fact changes everything. Let's begin with that box. Our goal is to make it perfectly empty. The first step is to remove the air. With a powerful pump, we could pull out every last atom. In the classical sense, the world of Isaac Newton and our daily lives, this is what we would call empty space. But it is not truly empty. Even the best vacuum on Earth has stray molecules. And it is filled with heat, which is just the motion of particles. So, we make the box colder, all the way down to absolute zero, the theoretical point where all classical motion stops. The atoms of the box itself would cease to vibrate. Now, surely, it must be empty. A space with zero matter and zero energy. For a long time, this was the accepted idea of a true vacuum. The lowest possible energy state. The definition of nothing. Then, in the early 20th century, a new theory emerged: quantum mechanics. It revealed a world that was not fixed and certain, but fuzzy and probabilistic. One of its most important discoveries came from a physicist named Werner Heisenberg. He described what we now call the Heisenberg Uncertainty Principle. The principle states that certain pairs of properties cannot be known with perfect accuracy at the same time. The more you know about a particle's position, for example, the less you can know about its momentum. The act of observing reality changes it. This is not a limit of our tools, but a fundamental feature of the universe itself. There is an inherent fuzziness to existence. This is where our definition of nothing begins to fall apart. The uncertainty principle also applies to energy and time. For incredibly brief moments, the total energy in a system can fluctuate, borrowing from the void and paying its debt back almost instantly. So even in our cold, empty box, something is still happening. The box is filled with what are known as quantum fields. In modern physics, every particle is an excitation in its own field, all of which permeate the entirety of space. The classical idea of a vacuum would be all these fields lying perfectly still. But the uncertainty principle forbids this. A field cannot have zero energy with perfect certainty. Instead, these fields are constantly simmering. Even in their lowest energy state, they are alive with what are called asterisk quantum fluctuations. The surface of our silent pond, at the quantum level, is a chaotic frenzy of microscopic waves. This is the quantum vacuum. It is not empty. It is alive. And from this fizzing sea of energy, particles emerge. For fleeting moments, a fluctuation can borrow enough energy to create a particle and its antimatter twin. An electron and a positron might pop into existence, exist for an instant, and then annihilate each other, returning their borrowed energy before the universe has time to notice. These are called asterisk virtual particles. They are not a mathematical trick. They are a constant, seething reality of the vacuum. The nothing inside our box is actually a chaotic dance of these ghostly particles. True, absolute emptiness is a state of theoretical fiction. A question remains. If these virtual particles appear and disappear so quickly, do they have any real effect? This is where the story moves from the theoretical to the observable. This energy of nothing has measurable, physical consequences. The most direct proof is a phenomenon known as the Casimir effect proposed by the physicist Hendrik Casimir in 1948. His thought experiment was simple. Imagine we take two perfectly smooth, uncharged metal plates and place them in our quantum vacuum, incredibly close to each other. The vacuum around the plates is a sea of virtual particles of all wavelengths. But between the two plates, things are different. The tiny gap allows only virtual photons of certain wavelengths to exist. Longer wavelengths are filtered out, they do not fit. The result is an imbalance. There are more available modes for virtual particles to exist in the space outside the plates than in the gap between them. This creates a pressure difference. The constant fizz of virtual particles from the outside is stronger than the fizz from the inside. And so, the plates are pushed together. This is not a speculative idea. This force has been measured with stunning accuracy. Scientists have observed a physical, tangible force being generated out of what we once considered absolute nothingness. The vacuum is not passive. It can push and pull. It has energy. This brings us to the heart of our original question. How does this energy have weight? The answer lies in Albert Einstein's equation, E equals mc squared. It reveals a deep connection. Mass and energy are fundamentally equivalent. And energy, like mass, has a gravitational effect. It warps spacetime. The energy of the vacuum, this zero-point energy of all the quantum fields, should therefore have a gravitational pull. Our box of nothing contains this energy. And because energy is equivalent to mass, that volume of nothing has a mass-equivalent value. It would, in a very real sense, tip the scales. A more precise statement would be that the lowest energy state of the universe is not zero. It is filled with a baseline level of energy, which has real consequences and contributes to the mass energy of the cosmos. The energy of the vacuum does not only matter on the smallest scales. When we look at the cosmos, we find it appears again, with magnificent and strange consequences. In 1917, Albert Einstein's theory of general relativity predicted that a universe full of matter should collapse under its own gravity. At the time, the universe was believed to be static, so Einstein added a cosmological constant to his equations. It was a fudge factor, an inherent energy of space itself that would create a gentle repulsive force to counteract gravity. When it was later discovered that the universe was expanding, Einstein abandoned the idea, calling it his biggest blunder. But the story did not end there. In 1998, astronomers observing distant supernovae made a discovery that changed our understanding of the universe. They expected to find that the expansion of space was slowing down due to gravity. Instead, they found the opposite. The expansion of the universe is accelerating. Something is actively pushing everything apart, acting like a kind of anti-gravity. Scientists gave this mysterious influence a name, dark energy. And the simplest candidate for what dark energy might be is Einstein's old, discarded idea: a constant, background energy density of the vacuum itself. The energy of nothing seems to be pushing space apart. This is where things get truly strange. Cosmologists can measure the effects of dark energy and calculate its value. It is tiny, unimaginably small, but quantum field theorists can try to calculate what the vacuum energy should be, based on the sum of all the quantum fluctuations. When they do, they get a number that is catastrophically wrong. Their prediction for the energy density of the vacuum is about 10 to the power of 120 times larger than the value we actually observe. This disagreement, known as the cosmological constant problem has been called the worst theoretical prediction in the history of physics. It is a quiet reminder that our two most successful theories of reality, general relativity and quantum mechanics, are fundamentally incomplete. They do not speak the same language when it comes to the energy of empty space. No one knows why this discrepancy exists. Perhaps there is an unknown symmetry that causes nearly all of this immense energy to cancel itself out. Whatever the solution, the implication is staggering. Roughly 68% of the known universe appears to be made of this mysterious dark energy. The nothing between the stars is the dominant player on the cosmic stage, dictating the ultimate fate of our universe. If this acceleration continues, in the distant future, all other galaxies will be pushed so far away that their light can never reach us. The sky will become dark and empty, leaving our own galaxy alone in an endless, accelerating void. The story of the vacuum is still being written. In laboratories, physicists are learning not just to observe it, but to manipulate it. This leads to an exotic concept called the squeezed vacuum. The quantum vacuum is full of fluctuations, a kind of baseline noise. Physicists have found a way to squeeze this uncertainty, reducing the noise in one property of light at the expense of increasing it in another. This has practical applications. The LIGO experiment, which detects gravitational waves, uses squeezed light to make its detectors sensitive enough to hear the faint ripples in spacetime from colliding black holes. They are manipulating the nothingness to listen to the whispers of the cosmos. Recent experiments have gone further, confirming that these vacuum fluctuations can be coaxed into producing real, measurable particles under specific conditions. While this does not mean free energy is possible, the process requires careful setup. It confirms that the vacuum is a dynamic, accessible part of our reality. If manipulating the vacuum is strange, the idea of destroying it is stranger still. One theoretical possibility, from the realm of string theory, is the bubble of nothing. This idea suggests our universe might have extra, hidden dimensions of space. In theory, one of these tiny dimensions could spontaneously collapse. If this happened, it would create a bubble expanding at the speed of light. Inside, there would be no space, no time, no reality as we know it. The bubble would simply erase the universe as it grew. This is an idea that exists at the very edge of our theories. The fact that our universe has survived for 13.8 billion years suggests our vacuum is probably stable. But the fact that our best theories can even describe the annihilation of spacetime, originating from an instability in the vacuum, shows just how central the concept of nothing has become. So we return to our box on the scale. We began with a simple question and found that nothing, as we imagine it, a state of passive emptiness, is an impossibility. The universe is never, and can never be, turned off. We discovered that the vacuum of space is not a silent void, but a roaring sea of energy and virtual particles. We found proof of its power in the Casimir effect, and we saw how this same energy, on a cosmic scale, becomes the dark energy pushing our universe apart. That box on the scale doesn't just hold an empty space. It holds the residual hum of creation, the engine of cosmic expansion, and the very fabric of reality itself. The next time you look up at the night sky, at the seemingly empty blackness between the stars, remember what is really there. It's not nothing, it's almost everything. The 2,000-year war over nothing. For a very long time, some of the most thoughtful minds in history held a quiet agreement. That a space could be truly, perfectly empty, was simply not possible. The idea itself felt like a contradiction, something that went against the very nature of the world. To suggest a space could hold absolutely nothing was to touch on an idea that felt deeply wrong. This is the story of that forbidden idea. A quiet struggle that lasted for 2,000 years, carried out not with weapons, but with simple glass tubes, metal spheres, and new ways of thinking. It's a story about the existence of nothing. And what we would eventually find, nothing, to be would turn out to be stranger, more powerful, and more important for the life of our universe than anyone could have imagined. This is the story of how we learned that the nothing we were once so hesitant to accept is actually a key to understanding almost everything. Imagine looking out into the quiet, dark space between galaxies. It looks like the most complete and perfect nothing we can imagine. For centuries, it was believed that was just an illusion, that space could never really be empty. But the truth is something quieter and stranger. That nothing has a kind of weight. It holds energy. It creates a physical force, gently pushing and pulling on the universe itself. And maybe strangest of all, this simmering, energetic nothing is what seems to be driving the entire cosmos apart. To understand how we went from thinking the void was impossible to realizing it shapes our universe, we have to go back to the beginning. To the thinker whose ideas on nothing would last for 2,000 years. In the intellectual world of ancient Greece, around the 4th century BC, a philosopher named Aristotle walked the earth. His influence was so deep, his logic so persuasive, that his ideas were often treated not as theories but as settled facts. And one of his most powerful ideas was this: horror vacui. Nature abhors a vacuum. To Aristotle, the thought of a void, a space with nothing in it, was not just physically unlikely, but it didn't seem to make logical sense. His reasoning was elegant and, for its time, felt very intuitive. Think about motion. An arrow flies because the air it displaces at the front rushes around to fill the space behind it, pushing the arrow along. In a true vacuum, what would cause an object to ever stop moving? There would be no resistance. Why, Aristotle reasoned, would it stop here instead of there? Without any medium to move through, it would seem it would either have to move forever or not move at all. Motion, in Aristotle's universe, needed something to happen in. This was a cornerstone of his understanding of the cosmos. The world, as he saw it, was a plenum, a space that was completely full. There were the four elements of the world: earth, water, air, and fire, and each had its natural place. Earth and water moved downwards while air and fire moved upwards. But what about the heavens? The space between the moon and the stars couldn't be made of these earthly elements. So, Aristotle proposed a fifth element, a perfect and invisible substance called ether. This celestial material filled all of space, making sure that no part of the universe was ever empty. Before Aristotle, there had been other ideas. Thinkers like Leucippus and his student Democritus imagined a universe made of just two things: indivisible particles they called atoms, and the empty space, the void, that the atoms moved through. It was a remarkable thought, but it was just an idea, a philosophy without proof. Against the careful logic of Aristotle, this atomic theory did not last. His dismissal of the vacuum was so complete and so authoritative that it became more than a scientific idea, it became dogma. For the next 2,000 years, through the Roman Empire, the Islamic Golden Age, and into medieval Europe, Aristotle's view was paramount. The idea of horror vacui was woven into natural philosophy and even theology. The universe was seen as a divine and perfect creation, and a hole in it, a place with no substance, seemed to suggest an imperfection. To challenge this was not just to disagree with an ancient philosopher, it was to question the very order of the cosmos. And so, for 2 millennia, the void was considered impossible. For centuries, Aristotle's idea of a full universe remained in place. The first questions would not come from a philosophical debate, but from a simple, practical problem: how to get water out of the ground. By the early 17th century, large engineering projects were underway in Europe. Deep mines were being dug, and elaborate fountains were being built. These projects often relied on a technology called the suction pump. It worked by drawing a piston up a long pipe, and water would rise to fill the space, as if pulled up by the vacuum itself. It seemed like a perfect example of horror vacui in action. Nature, disliking the empty space, filled it with water. But there was a strange limit. Miners and engineers found that no matter how powerful the pump, they could not lift water more than about 10 meters or 34 feet. The water would rise to that height and then stop. Why? What was it about 10 meters that made nature suddenly stop abhorring the vacuum? This puzzle was even a challenge for Galileo Galilei. He suggested that nature's abhorrence of a vacuum might have a limit, like a rope that can only hold so much weight before it breaks. It was an adjustment to the old theory, but it didn't feel like a complete answer. The real shift in understanding would come from one of Galileo's own followers, an Italian physicist named Evangelista Torricelli. Around 1643, Torricelli was thinking about this problem. He began to suspect the entire idea was backward. What if the water wasn't being pulled up at all? What if it was being pushed up from below? He had a new thought. What if we are all living at the bottom of a deep ocean of air? What if the air itself has weight, and that weight is pressing down on everything, including the surface of the water in a well? In this new picture, a suction pump doesn't create a pull. It just removes the air from inside the pipe. With no air pressing down on the water inside the pipe, the full weight of the atmosphere is still pressing down on the water outside the pipe. It is this outside pressure that pushes the water up, until the column of water inside becomes heavy enough to balance the weight of the air outside. The 10-meter limit wasn't a breaking point. It was simply the height where the weight of the water perfectly balanced the weight of the atmosphere. To test this, Torricelli designed an elegant experiment. Water required a very tall pipe, so he chose to work with mercury, a liquid about 13.5 times denser than water. If his theory was correct, the atmosphere should only be able to support a column of mercury that was much shorter. The procedure was simple. He took a glass tube about a meter long, sealed at one end, and filled it with mercury. Placing a finger over the open end, he turned the tube upside down and placed it in a dish also filled with mercury. When he removed his finger, some of the mercury flowed out, but it did not all flow out. It stopped, leaving a column of mercury standing about 760 millimeters high. And in the space above the mercury, at the sealed end of the tube, there was nothing. It was a space without mercury and without air. It was the first sustained, human-made vacuum. That empty space, the Torricellian vacuum, was a silent refutation of 2,000 years of thinking. But one more piece of evidence was needed. If the mercury was held up by the weight of a sea of air, then the column should be shorter at a higher altitude, where the sea of air would be shallower. A French scientist named Blaise Pascal devised a test. In 1648, Pascal, who was in poor health, asked his brother-in-law, Florent Perrier, who lived near a large mountain, the Puy de Dôme, to carry out the experiment. He asked him to measure the height of the mercury at the base of the mountain, and then carry the device to the top and measure it again. On September 19, 1648, Perrier and a small group of observers did exactly that. They set up the barometer in town, noting the height of the mercury. Then, they began the long climb up the mountain. At the summit, they assembled the apparatus again. The result was just as Pascal had predicted. The column of mercury was significantly lower, by over 80 millimeters. They had shown that the air had weight, and that this weight decreased with altitude. The sea of air was real. Aristotle wasn't just mistaken. His view of the world was built on a flawed starting point. The horror vacui was gone. Nature, it turned out, did not abhor a vacuum. The vacuum was real, and its existence was governed by the simple, measurable weight of the air. An idea known to only a few scholars is not enough to change the way people see the world. For that to happen, the vacuum needed to be demonstrated in a way that was simple, grand, and unforgettable. And the person to do that was a German scientist and mayor named Otto von Guericke. Von Guericke was fascinated by the work of Torricelli and Pascal, and he wanted to show the power of the vacuum in a way no one could forget. Around 1650, he invented a new, more effective air pump that could remove the air from a sealed container. With his pump, he began a series of demonstrations. He showed that in a vacuum, a candle flame goes out. He showed that a ringing bell inside an evacuated jar becomes silent, proving that sound needs a medium like air to travel. But these were preparations for his main demonstration. The event took place in 1654 in the town of Regensburg. Von Guericke had built two large copper half-spheres, designed to fit together to form an airtight seal. In front of the emperor and other officials, he placed the two halves together to make a single sphere. Then, he used his pump to remove the air from inside. What happened next was a quiet spectacle. Von Guericke attached a team of horses to each hemisphere and had them pull in opposite directions. The horses strained, but the hemispheres did not move. They were held together by an invisible, immense force. In one demonstration, a total of 30 horses were used, 15 on each side, and still, they could not separate the spheres. The force holding them was not some magic inside the sphere. It was the world outside it. With the air removed, there was no longer any internal pressure pushing the hemispheres out. But the full weight of Earth's atmosphere was still pressing in on them from all sides. It was the same principle Torricelli had discovered, but shown on a scale of raw power. The hemispheres weren't being held together, they were being crushed together by the weight of the air. Then, for the final demonstration, von Guericke opened a small valve. Air rushed back in with a hiss. The pressure inside and outside became equal, and the two hemispheres, which had resisted the strength of 30 horses, simply fell apart. The Magdeburg hemispheres experiment was a powerful piece of scientific theater. It showed that the nothing inside the sphere was not a source of pull, but simply the absence of a push, which allowed the very real push of the outside world to be seen. Inspired by this, Robert Boyle and Robert Hooke in England built a better air pump they called their pneumatical engine. Unlike von Guericke, who focused on public displays, Boyle was interested in systematic, repeatable experiments. He and Hooke carefully studied the properties of the air and the vacuum, and they were able to show that if you double the pressure on a gas, you have its volume. This simple relationship became known as Boyle's law. It turned the study of air into a quantitative science. The vacuum was no longer just a curiosity, it was something measurable and predictable. The work of the 17th century had shown that a vacuum could exist here, on Earth. But a question remained about the heavens, the vast, quiet space between planets and stars. Aristotle's old idea of a space-filling substance was about to return in a new form: the luminiferous ether. By the 19th century, scientists understood that light behaved like a wave. Experiments had shown that light could bend and interfere, all behaviors of waves. This created a puzzle. All known waves, sound in the air, ripples on water, needed something to travel through. A wave is a disturbance in something. So, if light was a wave, and it could travel from distant stars to Earth through what seemed to be empty space, what was the something it was waving in? To solve this, physicists imagined an invisible, massless, and perfectly transparent substance that filled all of space. They called it the luminiferous ether, the light-bearing ether. It had to be incredibly stiff to support the high speed of light, yet so thin that it didn't slow the planets as they orbited. It was a substance with contradictory properties, but it seemed necessary. The great question was not if the ether existed, but how to detect it. If the Earth is moving through this stationary sea of ether, it should create an ether wind. This wind should affect the speed of light. A beam of light traveling with the wind should move slightly faster than a beam traveling against it. Detecting this tiny difference required an experiment of almost unimaginable precision. This was the task taken on by two American physicists, Albert Michelson and Edward Morley. In 1887, at what is now Case Western Reserve University, they built a remarkable instrument called an interferometer. The idea was to split a beam of light, send the two halves on a race against each other at right angles, and then bring them back together. If an ether wind existed, one beam would be traveling slightly more against the wind than the other, and it would arrive a fraction of a second later. This would create a specific shift in the interference pattern where the beams recombined. They took incredible care to ensure accuracy. Their setup was built on a massive sandstone slab, which was then floated in a trough of mercury to quiet any possible vibrations. They had built an instrument more than sensitive enough to detect the tiny, expected shift. After countless observations, they had their result. It was a deep and profound puzzle. There was no shift. No matter how they turned the apparatus, the interference pattern remained quietly, infuriatingly fixed. The race was always a perfect tie. They had looked for the ether wind and had found nothing. The result was a clear, experimental fact that contradicted the most fundamental theory of light. The result of the Michelson-Morley experiment left physics with a difficult question. The answer, when it arrived, did not come from a famous university or laboratory. It came from a young patent clerk in Switzerland who had a habit of rethinking things from the very beginning. His name was Albert Einstein. In 1905, Einstein published a paper that didn't try to explain away the experiment or save the ether. He did something much more fundamental. He accepted the result as a simple truth and rebuilt physics from that point. He started with two principles. First, that the laws of physics are the same for all observers in uniform motion. Second, and this was the radical part, he proposed that the speed of light in a vacuum is the same for all observers, no matter how they or the light source are moving. This second idea took the failure of the Michelson-Morley experiment and turned it into a law of nature. If the speed of light is always constant, of course their experiment would find no difference. The light in both arms of their device would always have the exact same speed. The reason they couldn't detect an ether wind was because there was no ether wind to detect. With this, Einstein made the ether unnecessary. Light did not need a medium. Space could just be empty. This was the final step in the classical understanding of the vacuum. Aristotle's full universe was gone from the earth, and now its last ghost, the ether, was gone from the heavens. The vacuum, it seemed, had finally found its place as a simple, empty stage. But this quiet, simple emptiness was about to meet a new kind of science, one that would reveal this: nothing was not empty at all. For a short time in the history of physics, the vacuum was simple. Thanks to Einstein, it was just empty spacetime. But that simplicity would soon change. A new science was developing, one that worked on the smallest scales of reality. It was called quantum mechanics. And according to this science, the idea of a truly quiet, empty nothing is not how the universe works. The real vacuum is a chaotic, simmering, and energetic place. To understand why, we have to let go of our everyday intuition. In the quantum world, there is a fundamental uncertainty. The Heisenberg Uncertainty Principle states that you cannot know certain pairs of properties of a particle perfectly at the same time. This principle also applies to energy and time. It means that for very short moments, energy can, and does, spontaneously emerge from nothing before quickly disappearing again. This idea is part of what's known as quantum field theory. This theory describes the universe as being filled with different fields: an electron field, a photon field, and so on. A particle is just a small, localized vibration in its field. When you remove all the particles from a space to create a vacuum, you might think the fields would all become perfectly flat and still. But they don't. Because of the uncertainty principle, a quantum field can never be perfectly zero. Even in its lowest possible energy state, its ground state, a field is still humming with a minimum amount of energy. This is called the zero-point energy. Think of it like the surface of an ocean. From a distance, it might look perfectly flat. But if you look closer, you see it is always moving with tiny ripples. The vacuum appears to be similar. It looks calm on our scale, but at the quantum level, it is a quiet foam of energy fluctuations. These fluctuations can even appear as pairs of virtual particles, a particle and its antiparticle, that pop into existence, exist for an unimaginably short time, and then vanish. The vacuum, then, is not empty. It is filled with a quiet foam of these virtual particles, constantly appearing and disappearing. For a long time, this was a strange but theoretical idea. How could you prove this background energy was real? Even today, experiments at places like the star detector at Brookhaven National Laboratory are finding new ways to probe this quantum world, looking at the subtle ways these virtual particles behave. And in 1948, a Dutch physicist named Hendrik Casimir suggested a way to make this invisible energy reveal itself as a real, tangible force. In 1948, Hendrik Casimir proposed something that seemed deeply counterintuitive. He suggested that if you take two perfectly flat, uncharged metal plates and place them very close together in a vacuum, a force will emerge from the nothing between them and gently push them together. This idea, the Casimir effect, is a direct result of the energetic nature of the quantum vacuum. Let's return to the idea of an ocean of quantum fluctuations. Now, imagine placing two large ships parallel to each other on this restless water. In the open sea around the ships, waves of all sizes can exist. But in the narrow space between the ships, things are different. A very long wave simply cannot fit. Only waves whose wavelengths fit neatly into the gap can exist there. The result is a subtle pressure imbalance. There are more possible wave patterns on the outside of the ships than on the inside. The net effect is that the ships are pushed together, not by a conventional force, but by the quiet absence of certain waves between them. The Casimir effect is the same principle. The two parallel plates restrict the wavelengths of virtual particles that can exist between them. This creates a slight pressure difference in the vacuum energy itself. The greater pressure of the vacuum on the outside of the plates pushes them together. For decades, this Casimir effect remained a theoretical idea, the force thought to be too small to ever measure. As technology improved, allowing for the measurement of incredibly small forces, the experiment became possible. In 1997, one of the most compelling confirmations was achieved by physicist Steve Lamoureux. The force was real. It was a measurable force, emerging from the empty vacuum. Nothing, it seemed, had a gentle push. We started with a universe where nothing was forbidden, and have arrived in a universe where nothing is a quiet foam of virtual particles. This story doesn't end here. This strange energy of the void doesn't just act on tiny metal plates in a lab. It acts on the largest possible scale, and may hold the key to the fate of our own universe. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The confirmation of the Casimir effect showed that the vacuum holds energy. It's a real, physical property of empty space. This opened a much larger question. Could this vacuum energy affect the universe on a cosmic scale? According to Einstein's theory of general relativity, the answer is yes. Energy and mass both curve spacetime, which is what we feel as gravity. So, the energy of the vacuum should have a gravitational effect. But it's a strange kind of effect. While normal matter pulls things together, the quantum vacuum's energy is predicted to have a kind of negative pressure. This negative pressure acts as a repulsive force, an anti-gravity that pushes space itself apart. For most of the 20th century, this was a theoretical curiosity. Then, in 1998, everything changed. Two different teams of astronomers studying distant supernovae made a quiet but profound discovery. The expansion of the universe was not slowing down because of gravity, as everyone had expected. It was speeding up. Something was acting like a cosmic accelerator, pushing everything apart faster and faster. Scientists gave this mysterious influence a name: dark energy. And the leading candidate for what dark energy is the energy of the vacuum. That same strange, repulsive force predicted by quantum mechanics seems to be at work on a cosmic scale, making up an estimated 68% of all the energy in the universe. But this simple picture comes with what has been called the worst theoretical prediction in the history of physics. When theorists try to calculate how strong this vacuum energy should be based on quantum field theory, the number they get is enormous. It is 120 orders of magnitude, a 1 with 120 zeros after it, larger than the value we actually observe. If the vacuum energy were truly that powerful, the universe would have been pushed apart in the first moments of its existence. This deep discrepancy, known as the cosmological constant problem, is one of the most profound mysteries in all of science. Why is the measured value of the vacuum energy so incomprehensibly small, so quiet, compared to the theoretical prediction? Is there some other law of nature that cancels almost all of it out? The long journey to understand nothing has brought us here. We began with Aristotle, for whom the void was an impossibility. We saw thinkers like Torricelli and von Guericke show that it was real. We watched Einstein clear away its last ghost, the ether, only for quantum mechanics to reveal that the void was secretly full of quiet energy. And now, we find ourselves in a universe where that same energy seems to be guiding its future, yet in a way we are deeply unable to explain. The story of nothing has, in its own way, become the story of almost everything, a journey from a simple question to one of the deepest mysteries we now face. The search may be over, but the quiet, unanswered question of what nothing truly is, remains. Your entire reality is just ripples in a field. Take a moment to look at your hand. It appears solid. It feels real. You can knock it against a table, and the sound that returns seems to confirm the distinct, separate existence of both things. For most of our lives, we operate on a quiet, intuitive assumption that the world is made of objects, built from smaller and smaller pieces of matter. But that simple assumption, the very foundation of how we perceive reality, is incomplete. Not in a philosophical sense, but in a physical one. Your hand, the table, and everything you can touch are not truly solid. You are not a collection of particles, so much as a persistent, complex pattern. A pattern not unlike ripples on a vast, invisible ocean that fills every part of existence. The most solid thing you know is mostly empty space. And the stuff inside that space is less like a thing and more like a quiet disturbance. A collection of ripples in a field. Today, we journey to the foundation of reality itself, to explore the idea that we are made not of particles, but of the fields from which they arise. And in doing so, we will find that the strangest energy in the universe is hidden in what we call empty space. The end of things. Our quest to understand the universe has often been a story of division. The ancient Greek philosopher Democritus imagined that if you took a piece of matter and cut it in half, again and again, you would eventually reach a final, uncuttable piece. He called this atomos, meaning uncuttable. It was a powerful idea that echoed for centuries, painting a simple picture of the world. A grand structure made from fundamental, indestructible bricks. For a long time, this was the dream. Isaac Newton's physics described a clockwork universe, where tiny, solid balls of matter, from planets to atoms, followed precise, predictable laws. They were definite, they were real, they were things. The 20th century, at first, seemed to be the final confirmation of this idea. We found atoms, and then we broke them open. Inside, we found even smaller particles, electrons, protons, and neutrons. Then we broke those open, and found that protons and neutrons were themselves made of even smaller motes of matter called quarks. This work culminated in one of the most successful theories in all of science, the Standard Model of particle physics. It is our modern catalog of the fundamental bricks of reality. It tells us that with just a handful of quarks, a few leptons like the electron, and the particles that carry forces, we can build almost everything we see. It's an intellectual triumph. It's elegant, it has been tested with incredible precision, and it feels like the final validation of that 2,000-year-old dream. And yet, this beautiful, intuitive picture, the one most of us learn in school, is a shadow of the truth. It is a convenient story we tell ourselves, because the real nature of things is far stranger than our minds are built to easily comprehend. The first signs that something was deeply wrong with this particle-centric view began to appear over 100 years ago. They came not as a single discovery, but as a series of quiet, unsettling paradoxes that threatened to unravel physics itself. The age of asterisk things was coming to a gentle end. The universe gets weird. The first crack in the solid foundation of classical physics appeared in the dark. At the turn of the 20th century, physicists were studying a seemingly simple problem: black body radiation, or why hot objects glow. The established physics of the time made a prediction, and that prediction was an absolute disaster. It suggested that any hot object should radiate an infinite amount of energy, instantly shedding its heat in a flood of high-frequency light. This was obviously wrong, and it was nicknamed the ultraviolet catastrophe. It was a quiet signal that the trusted laws of physics were failing. Then there was the problem of the atom itself. After it was discovered that atoms had a dense nucleus with electrons orbiting it, classical physics again made a strange prediction. An orbiting electron should continuously radiate away energy as light. As it lost energy, its orbit would decay. Within a fraction of a second, every electron in every atom should spiral into the nucleus, annihilating all matter. The fact that you, the world around you, and the entire universe still exist is daily, second-by-second proof that this classical picture is incomplete. But the deepest mystery, the one that truly challenged our idea of particles as tiny, solid balls, is the double-slit experiment. Imagine a barrier with two thin slits in it. If you fire a stream of electrons at this barrier, and you watch to see which slit each electron goes through, you get what you would expect: two distinct bands on a detector screen behind the barrier. It is as if you were throwing marbles through two holes. But this is where it gets strange. If you remove the detectors and simply let the electrons fly, something impossible seems to happen. You don't get two bands. You get a pattern of many bands, an interference pattern. This is the signature of a wave. It is what happens when a wave passes through both slits at once and interferes with itself. A single electron, when unobserved, appears to go through both slits at the same time and interfere with itself, as if it were a wave. It's as if a single marble passed through both holes simultaneously and then landed in multiple places on the other side. This phenomenon, known as wave-particle duality, was the final nail in the coffin for the simple picture of a particle. Particles were not just little balls. They had a ghostly, contradictory, wave-like nature that defied all common sense. This was not a metaphor. It is an experimental reality, confirmed time and time again. An unobserved electron isn't in any single place. It exists as a cloud of probabilities, a wave function that only collapses into a definite particle at the moment you measure it. This was the great puzzle that quantum mechanics had to solve. If particles aren't really things until we look at them, then what is the fundamental stuff of the universe? The answer would require a complete rebuilding of our understanding, starting not with the particle, but with the empty space it moves through. The ocean of being. For decades, physicists grappled with the strangeness of wave-particle duality. The solution that matured from their work was as profound as it was elegant. It's called quantum field theory, or QFT, and it is arguably the most successful physical theory ever created. QFT makes a quiet, but radical proposition. The most fundamental component of the universe is not the particle. It is the field. The word field may sound abstract, but you experience fields every day. When you drop something, it falls because the Earth creates a gravitational field that permeates the space around it, telling the object how to move. You cannot see the field, only its effect. A more visual example is a magnetic field. If you sprinkle iron filings around a magnet, they trace invisible lines of force. The filings are not creating the pattern. They are asterisk revealing a pattern that already exists in space. The field is a property of space itself. Classical physics knew about these fields. But quantum field theory took this idea and applied it to everything. It asked, what if, for every type of particle we know, there is a corresponding field that extends throughout all of space and time? This is the revelation. There is an electron field, and it is everywhere. And what we call an electron is nothing more than a localized vibration, a ripple, a tiny excitation in that electron field. Perhaps the best analogy is to think of a perfectly calm, infinite ocean. That ocean represents a field in its lowest energy state. Now, if you tap the surface, you create a ripple. That ripple is a particle. The wave isn't a separate thing moving on the water. The wave is the water, just in a more excited state. In the same way, an electron is not a thing moving through the electron field. The electron is a ripple of the electron field. The field is the fundamental reality. The particle is just a temporary manifestation of it. This concept resolves the paradox of wave-particle duality. Of course, an electron can behave like a wave, because fundamentally, it is a wave in its underlying field. When we observe it, we interact with the field at a specific point, causing its energy to localize, and we register a particle. When we don't observe it, the wave propagates and can do wavy things, like pass through two slits at once. This applies to everything. There is a photon field. A ripple in this field is a photon. There are up quark fields and down quark fields. Ripples in these are the quarks that make up our world. For every particle in the Standard Model, there is a corresponding ocean that fills all of reality. Our universe is not a collection of tiny billiard balls. It is a superposition of interacting, interwoven quantum fields. You, me, the stars, we are all just incredibly complex, stable symphonies of ripples on these cosmic oceans. The particles that make you up are not solid bits of matter. They are localized vibrations of fields that connect you to the furthest reaches of the cosmos. The sound of silence. If the entire universe is filled with these invisible fields, it raises a profound question. What, then, is empty space? What is a vacuum? In the old, particle-centric view, a vacuum was simply the absence of things. But in the world of quantum field theory, this picture is impossible. A vacuum isn't the absence of everything. It is simply the state you have when all the fields are in their lowest possible energy state. It is the fields at rest. But here is the twist that changes everything. In the quantum world, at rest does not mean perfectly still. This is a command, issued by one of the deepest principles of nature, the Heisenberg Uncertainty Principle. One version of this principle states that you cannot know the exact energy of a system over a finite amount of time. The shorter the time interval you look at, the more uncertain the energy becomes. If we apply this to a patch of empty space, we see a problem. If we were to say that the energy of the vacuum is exactly zero, and always zero, we would be violating the uncertainty principle. We would be claiming to know its energy perfectly at every single instant. Quantum mechanics forbids this. This means that the energy of a field, even in a vacuum, can't be perfectly and constantly zero. It must fluctuate. The cosmic oceans can never be perfectly flat. They must always have a subtle, underlying tremor, a ceaseless hum of energy that can never be silenced. This is zero-point energy. It is the energy of nothing. It is the baseline energy of the universe that exists even at absolute zero temperature, where all classical motion should stop. Every field, the electron field, the photon field, all of them, has a zero-point energy. This means that what we call a vacuum is not a peaceful void. It is a plenum, a dynamic and energetic medium that underpins all of existence. And this constant thrum of energy does not just sit there. It does something utterly astonishing. Ghosts in the machine. The realization that empty space is humming with a baseline energy leads to an even stranger consequence. Because the energy of these quantum fields is constantly fluctuating, every once in a while, for an infinitesimally short moment, the energy in a tiny patch of space can spike. If the energy spike is large enough, the field can borrow this energy from the void to create a particle and its corresponding antiparticle, seemingly out of thin air. This is the world of virtual particles. This process is governed by the time and energy version of the uncertainty principle. A field can borrow enough energy from the vacuum to create, for instance, an electron and its antimatter twin, a positron. This pair exists for a fleeting moment before they find each other and annihilate, paying back the energy to the vacuum. The more energy that is borrowed, the faster it must be returned. This is not a rare occurrence. It is happening everywhere, all the time, in every cubic centimeter of space around you. The nothingness of empty space is, in reality, a foaming, bubbling soup of these virtual particle pairs, constantly emerging and vanishing. They are called virtual because they don't last long enough to be directly observed as stable particles. They are temporary disturbances, not persistent ripples. But just because they are temporary does not mean they are not real. Their existence has measurable consequences. One of the most important is called vacuum polarization. Imagine a real electron traveling through the vacuum. Its negative charge will slightly repel the virtual electrons and attract the virtual positrons in the bubbling soup around it. This creates a tiny, fleeting shroud of positive charge around our bare electron. This shroud effectively screens the electron's true charge, meaning the charge we measure from a distance is slightly weaker than its charge up close. This effect has been measured with incredible precision. The properties of the hydrogen atom, for instance, can only be calculated correctly if you account for the way its electron interacts with the sea of virtual particles in the vacuum. These fleeting echoes are real, and their whispers shape the world we see. But physics demands more than whispers. It demands proof. And in the 20th century, physicists devised experiments to prove that the energy of the void was not just a mathematical idea. Proof from the void. For a long time, the idea of a vacuum boiling with energy sounded like science fiction. How can you measure the energy of nothing? The answer came in 1948 from the Dutch physicist Hendrik Casimir. His idea, the Casimir effect, is a brilliant and direct demonstration of zero-point energy. Imagine taking two perfectly flat, uncharged metal plates and placing them parallel to each other in a perfect vacuum. Classically, nothing should happen. But Casimir realized that the sea of virtual particles would behave differently between the plates than outside them. Outside the plates, virtual particles of all wavelengths can exist. But the tiny gap between the plates acts as a constraint. Only virtual particles whose wavelengths fit neatly into that gap can exist there. This means there are more energetic fluctuations allowed to exist outside the plates than inside. This imbalance creates a pressure. The greater energy of the vacuum outside literally pushes the plates together. For decades, this was a prediction. But in 1997, an experiment led by physicist Stephen Lamoureux successfully measured this tiny force, and his results matched the prediction. It was the first experimental confirmation that the vacuum has energy, and this energy can exert a real, physical force. Later experiments have confirmed the effect with even greater precision. A second, more exotic piece of evidence comes from the cosmos. In 2017, astronomers observing a neutron star with an incredibly strong magnetic field noticed something unusual about its light. The best explanation for what they saw is that as the light traveled through the empty space around the star, the intense magnetic field excited the virtual particles in the vacuum, causing the vacuum itself to act like a prism and alter the light. It is compelling evidence that empty space, when stirred, can change the properties of the universe passing through it. Physicists have also long theorized about the Schwinger effect, the idea that a strong enough electric field could literally pull a particle-antiparticle pair out of the vacuum and make them real. While achieving this from a true vacuum is still beyond our technology, a remarkable 2022 experiment gave us a glimpse of a related phenomenon. Researchers used graphene to create an immense electric field within the material. Under these conditions, they observed the spontaneous creation of electron-hole pairs, the solid-state equivalent of particle-antiparticle pairs. They were, in a sense, pulling excitations out of the simulated vacuum of the material. It was a powerful demonstration of how energy can be converted into particles, reinforcing the idea that the vacuum is not a void, but a substance laden with potential. The cosmic question mark. We have established that the vacuum is not empty. It seethes with a baseline energy, the zero-point energy, proven to exist by laboratory experiments. But this discovery opens up one of the deepest and most humbling problems in all of modern physics: the cosmological constant problem. According to Einstein's theory of general relativity, energy curves spacetime, which we experience as gravity. Since the vacuum has energy, it should have a gravitational effect. It should act as a form of anti-gravity, pushing the universe apart. When physicists use quantum field theory to calculate how much zero-point energy there should be, the answer they get is catastrophically enormous. If this calculation were correct, the repulsive force of the vacuum should have been so powerful that it would have ripped the universe to shreds moments after the Big Bang. Galaxies and stars would never have formed. Obviously, that has not happened. We are here. To make matters stranger, in 1998, astronomers discovered that the expansion of the universe is, in fact, accelerating. There really is a mysterious force pushing everything apart, which we call dark energy. The problem is, the measured strength of this dark energy is about 120 orders of magnitude, a 1 followed by 120 zeros, smaller than the amount of energy our theories predict for the vacuum. This is, without exaggeration, the single largest discrepancy in the history of science. It means there is a colossal gap between our theory of the very small and our theory of the very large. There must be some unknown physical principle that is canceling out almost all of the vacuum's energy, leaving behind just a tiny, residual amount. We know the energy of the void is real. We have measured its effects. But we have absolutely no idea why it's not tearing the universe apart. It is the biggest question mark in all of science, a quiet reminder that the true nature of reality is still far beyond our grasp. If this kind of calm exploration into the nature of reality helps you unwind, consider liking the video and subscribing to the channel. And I have a question to leave with you. Does this idea of being a ripple in a field make you feel more connected to the universe, or does it make reality feel less solid and more illusory? Feel free to share your thoughts in the comments below. Let us return to where we started. Look at your hand one last time. It still appears solid. It still feels real. But now you know a deeper truth. It is not a collection of tiny, separate particles. It is a coherent, breathtakingly complex symphony of vibrations. A dance of ripples on a dozen different, overlapping quantum fields that fill all of space. The electrons in your atoms are ripples in the electron field. The quarks in your nuclei are ripples in the quark fields. The photons streaming into your eyes are ripples in the electromagnetic field. You are not a asterisk thing that exists within the universe. You are a dynamic process of the universe itself. A persistent pattern of energy, a self-aware collection of ripples on the fundamental fabric of existence. This does not make reality any less real. It makes it infinitely more profound. The distinction between you and the empty space around you is an illusion. The same fields that constitute your body extend outward to the farthest stars. You are, in the most literal sense, connected to everything. A temporary, thinking, feeling wave on the silent, energetic ocean of being. Empty space is a lie, the secret engine of reality. For centuries, the idea of a perfect vacuum has served as our definition of nothingness. An inert, silent, featureless void. A stage on which reality exists, but a stage that is, itself, empty. Modern physics, however, has quietly corrected this intuition. It has revealed a concept that forces a new understanding of reality. The nothing we imagine appears to be a source of immense energy, a constant state of activity shaping the world of atoms, and holding clues to mysteries of the cosmos. The foundational concept is that true empty space does not exist. The idea of absolute nothingness may be an illusion. This is an exploration of that illusion. We will look at the quantum rule that forbids perfect emptiness. We will examine the reality of the quantum foam, a world where phantom particles appear and disappear. And importantly, we will uncover the experimental proof showing this is not just a theory, but a measurable aspect of our universe. In the end, the space between things will look different. It will not appear as nothing. It will appear as a secret engine of reality itself. The anatomy of an illusion. To understand the illusion, we must first appreciate why it was so convincing. The concept of empty feels intuitive. We can begin with the atom. An atom has a small, dense nucleus with electrons in orbit. The scale is difficult to comprehend. If the nucleus of a hydrogen atom were the size of a marble in a large football stadium, the electron would be a speck of dust in the outer seats. Everything in between is described as empty space. Over 99.99999999999% of what we think of as solid matter is, by this definition, empty. This fact leads to the intuition that emptiness is a fundamental part of the universe. If we could remove all of the atoms, what would be left? We can scale up to interstellar space, far from any planets or stars. The density here is very low, about 1 atom per cc. It is almost a perfect vacuum by human standards. Further still, in the voids of intergalactic space, the vacuum is even more profound. The density drops to less than 1 atom per cubic meter. This is the emptiest place we know. In classical physics, this is how we arrive at the idea of a perfect vacuum. In the world of Isaac Newton, a vacuum is defined by what it does not have. Zero matter, zero particles, zero energy. The temperature is absolute zero, where all motion stops. It is a state of stillness, of nothing. For hundreds of years, this was the accepted picture. The vacuum was a passive backdrop. It did nothing. It was nothing. But as our understanding deepened in the 20th century, the first problems with this picture of nothingness began to appear. Astronomers realized that even the deep voids of space are not truly empty. They are filled with a tenuous presence of things. There is the cosmic microwave background, a faint light from the Big Bang that fills all of space. Stray neutrinos pass through the cosmos. There is even a sparse wind of particles streaming from galaxies. So, one might revise the definition. A true vacuum is not just a place with very little. It's a place where we have hypothetically removed everything, every atom, every photon, every neutrino. We shield it from all fields and cool it to absolute zero. Now, what's left must be nothing. The ultimate, perfect void. It is at this point, the point of supposed perfect emptiness, that our classical intuition breaks down. Because quantum mechanics presents a rule that is a fundamental law of reality. It declares that a state of perfect, tranquil nothingness is physically impossible. To understand why, we have to look at one of the most powerful principles in science. The rule that forbids nothingness. The reason perfect emptiness cannot exist comes from a fundamental principle of the quantum world, the Heisenberg Uncertainty Principle. It was formulated in 1927 by the German physicist Werner Heisenberg, and it changed the classical, deterministic view of the universe. In classical physics, it is believed we can know everything about an object at the same time. With a good enough ruler and stopwatch, one could measure a car's exact position and its exact speed at the same moment. Heisenberg's work showed this was not true at a fundamental level. Nature itself imposes a limit on what we can know. The principle states that there are pairs of properties of a particle, conjugate variables, that are linked. The more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This is not an issue with our measurement tools. It is a fundamental property of the universe itself. A particle does not possess a perfectly defined position and a perfectly defined momentum at the same time. Its nature is inherently fuzzy. A wave on the surface of a pond serves as an analogy. The question of its exact location is difficult to answer. A wave is, by its nature, spread out. To measure its wavelength, which is related to its momentum, you must observe it over a distance. But to know its position, you would focus on a single point, at which the concept of wavelength loses its meaning. Quantum particles have this wave-like nature. This principle also applies to another pair of properties, energy and time. The formula for this relationship is delta E multiplied by delta T is greater than or equal to a very small constant of nature. Delta E is the uncertainty in energy, and delta T is the uncertainty in a duration of time. The equation means you cannot know the exact energy of a system over a precisely defined interval of time. There is always a fundamental fuzziness. Let us return to our perfect vacuum. We defined it as a region with exactly zero energy. But if we say the energy is exactly zero, our uncertainty in energy, delta E, is also zero. For Heisenberg's equation to be true, this would mean the uncertainty in time, delta T, must be infinite. To be certain the energy is zero, you would have to observe it for an infinite amount of time. In other words, if you look at a point in empty space for a very short moment of time, making delta T very small, the uncertainty in its energy, delta E, must be large. The energy at that point cannot be zero. It is forced to fluctuate. It must be uncertain. This is a profound statement about the nature of reality. The universe does not permit any system, including empty space, to have a perfectly constant, definite energy of zero. The vacuum is therefore forbidden from being a state of nothingness. It must be a place of constant activity. This restlessness is the baseline state of existence. The question then becomes, what does this energy look like? The answer leads to one of the stranger concepts in physics: the boiling sea of reality. If the uncertainty principle forbids empty space from having zero energy, it must have something else. This is what physicists call vacuum energy or zero-point energy. Even at absolute zero, every point in space has a minimum, non-zero amount of energy. A fundamental activity that can never be silenced. But this energy is not static. It fluctuates. This is a process called quantum fluctuations. The uncertainty principle suggests that energy can be borrowed from the vacuum to create something from nothing, as long as that energy is returned to the vacuum almost instantly. The more energy is borrowed, the faster it must be returned. To understand this, we need to look at reality through quantum field theory. This theory does not see particles like electrons and photons as small solid objects. Instead, it describes reality as being made of invisible fields. There is an electron field that permeates all of spacetime. There is a photon field, and fields for every other known particle. What we think of as a particle is just a localized, excited ripple in its corresponding field. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. The vacuum, then, is the state where all of these fields are in their lowest possible energy state, their ground state. There are no stable, lasting ripples, which means there are no real particles. But because of the uncertainty principle, these fields can never be perfectly still. They are constantly fluctuating, even in their ground state. These tiny, temporary flickers in the fields are what we call virtual particles. For an extremely short moment, a fluctuation in the electron field might create what looks like an electron and its antimatter counterpart, a positron. They appear, exist for a fraction of a second, and then annihilate each other, vanishing back into the field. A virtual electron-positron pair might appear and disappear. A virtual quark-antiquark pair might do the same. This is happening everywhere, all the time. The vacuum, therefore, is not an empty stage. It is a dynamic environment, a bubbling sea of these phantom particles. The physicist John Wheeler gave this concept a name, quantum foam. The analogy is the fizz on a glass of soda. You see bubbles constantly forming and popping, a chaotic surface. Quantum foam is the idea that if you could see space-time at the smallest possible scale, the Planck length, you would not see a smooth, flat canvas. You would see space-time itself, warping and bubbling as virtual particles appear and vanish. It is important to address a misconception. The word particle in virtual particles can be misleading. They are not small objects that briefly become real. It is more accurate to think of them as disturbances in the fields. In the mathematics of quantum field theory, they are like bookkeeping devices. When two real electrons repel each other, we can visualize it as them exchanging a virtual photon. But what is really happening is that one electron's field creates a disturbance in the electromagnetic field, which then interacts with the other electron's field, pushing it away. Virtual particles are the language for interactions between fields. They are virtual because they are off-mass shell, meaning they do not have to obey the same energy-momentum rules as real, observable particles. But their effects are real. They are not just mathematical ghosts. They are the background activity of the universe. And this activity has real, measurable consequences. The foam is real, and there is proof. The ghosts in the machine. This concept of a vacuum filled with particles is not speculation. Its effects are observable and have been measured with precision. This is established, experimental fact. One of the most direct pieces of evidence is a phenomenon called the Casimir effect. Predicted by Dutch physicist Hendrik Casimir in 1948, the experiment is simple in concept but profound. Imagine two smooth, uncharged metal plates placed parallel to each other in a vacuum, extremely close together. Classically, you would expect nothing to happen. There are no charges, no significant gravity. They should remain still. This is not what is observed. Instead, a measurable force pushes the plates together. This force comes from the quantum foam. The vacuum is filled with virtual particles of all different wavelengths. Outside the plates, virtual particles of every possible wavelength can exist. But the small gap between the plates acts as a resonant cavity. It restricts which virtual particles can appear. Only virtual particles whose wavelengths fit into the gap can exist there. Longer wavelength virtual particles are excluded. This means there are more quantum fluctuations happening in the space outside the plates than in the space between them. This imbalance creates a pressure difference. The greater pressure of the quantum foam on the outside pushes the plates together. It is a physical force generated by the vacuum itself. The experiment has been done, and the measured force matches the theoretical prediction. Another piece of evidence comes from the atom itself. It is called the *Lamb shift. According to earlier quantum theories, certain electron orbitals in a hydrogen atom should have exactly the same energy level. The states known as 2s and 2p were predicted to be identical in energy. But in 1947, Willis Lamb and Robert Rutherford performed an experiment and discovered this was not true. The 2s state had a slightly higher energy level than the 2p state. The difference was very small, but it was there, a contradiction of the existing theory. The explanation came from the quantum vacuum. The electron orbiting the proton is moving through the quantum foam. It is constantly jostled by virtual particles. These interactions slightly change the electron's path and shift its energy level. Because the shape of the 2s orbital is different from the 2p orbital, it gets jostled slightly more, which raises its energy. When physicists calculated the effect of these vacuum fluctuations, their prediction for the energy shift matched the experimental measurement with high accuracy. This was an important confirmation for the theory of quantum electrodynamics, QED, and provided compelling evidence that the energy of empty space is real. There is more. The magnetic property of the electron, its magnetic moment, is also affected. Simple theory predicted a certain value, but experiments showed it was off by about 0.1%. This small discrepancy was perfectly explained by accounting for the cloud of virtual particles that constantly interacts with the electron. The theory of QED, including these vacuum effects, is now one of the most precisely tested theories in science. These are not just historical notes. Modern experiments continue to confirm the reality of vacuum energy. The sensitive detectors at LIGO, which detect gravitational waves, are so precise that their measurements are limited by the quantum noise of the vacuum. The effects of the vacuum are a practical problem for our most advanced instruments. The evidence suggests empty space is alive with energy. And this energy also plays a role on the scale of the entire cosmos. The engine of the cosmos. The implications of vacuum energy also appear on a cosmic scale. This is where this engine reveals its power. In the late 1990s, astronomers made a discovery that changed our understanding of the cosmos. They were using distant supernovae to measure the expansion rate of the universe. They expected to find the expansion was either slowing down due to gravity or was coasting at a steady rate. What they found was the opposite. The expansion of the universe is accelerating. The observation suggested something was pushing space itself apart, working against the gravity of all the matter in the universe. This was given a name, dark energy. It appears to be the most dominant thing in the universe. It accounts for nearly 70% of the cosmos's total energy content. Dark matter makes up about 25%, and all normal matter, every star and galaxy, is less than 5%. We live in a universe dominated by something we cannot see. The leading candidate for dark energy is the energy of the vacuum itself. The idea is that if empty space has an intrinsic, non-zero energy, this energy should have a gravitational effect. According to Einstein's theory of general relativity, energy can warp spacetime. While normal matter creates an attractive gravitational pull, the properties of vacuum energy would produce a repulsive one, a kind of anti-gravity. More space would mean more vacuum energy, which would mean a stronger push, leading to accelerating expansion. It fits the observations. The energy of the quantum foam could be the engine driving the cosmos apart. But this explanation comes with what is sometimes called the worst prediction in the history of physics. It is a mystery known as the cosmological constant problem or the vacuum catastrophe. Here is the problem. When theoretical physicists use quantum field theory to calculate how much energy the vacuum should have, they get a colossal number. An extraordinarily large number. Then, astronomers measure the actual strength of dark energy by observing the universe's acceleration. This gives them the observed value for the vacuum energy. When you compare the two numbers, they do not just disagree. They disagree by an amount that is difficult to describe. The predicted value is 10 to the power of 120 times larger than the observed value. That is a 1 followed by 120 zeros. To put that in perspective, there are only about 10 to the power of 80 atoms in the observable universe. This large discrepancy between the theory of the very small and the observation of the very large suggests that we are missing something fundamental in our understanding of how reality works. Why is the observed vacuum energy so small, yet not zero? Why does it have this specific, tiny value? No one knows. It is one of the biggest unsolved problems in physics. Some think there may be an unknown physical law that cancels out most of the vacuum energy. Perhaps our understanding of quantum field theory or gravity is incomplete. Recent data, like that from the Dark Energy Spectroscopic Instrument, DESI, is exploring whether dark energy is constant, or if it changes over time, which may hint at new physics. This catastrophe is not a failure. It is a sign pointing toward a new, deeper level of physics we have yet to uncover. It connects the world of the very small, the quantum foam, with the world of the very large, the fate of the universe. The engine is there, and we can see it working, but its manual is written in a language we do not yet understand. We began with the idea that empty space is nothing. We have explored the atom, intergalactic voids, and the quantum scale. And at each stage, that idea appears to be an illusion. There is no such thing as nothing. The Heisenberg Uncertainty Principle forbids it. The vacuum of space is a dynamic entity. It is an ocean of quantum fields, flickering with the energy of virtual particles. We call it the quantum foam. And this is not just a theory. We have seen its proof. We see it in the Casimir effect, where the vacuum exerts a physical force. We see it in the Lamb shift, where the quantum foam jostles electrons, changing their energy in a way that matches our predictions. We feel its effects in our most sensitive experiments. On the grandest scale, this energy of nothingness is our best candidate for the dark energy that is accelerating the expansion of our universe. The energy in every cubic centimeter of space seems to be the engine driving the cosmos, even as the scale of that energy remains a great mystery. So, the next time you look at the night sky, at the dark space between the stars, remember what you are seeing. You are not looking at an empty void. You are not looking at nothing. You are looking at a fundamental, active, and powerful component of the cosmos. An unseen architect, a silent engine, and our understanding of it is only just beginning. The quantum trick that lets geckos walk on ceilings. Some animals move through the modern world as quiet reminders that our rules are not the only rules. They seem to treat gravity less as a law and more as a gentle suggestion. You have seen them. A small lizard, skittering across a perfectly smooth window, or hanging from a ceiling, as comfortable as we are on solid ground. For more than 2,000 years, we watched the gecko and wondered. The philosopher Aristotle noted its ability to run up and down a tree in any way. It was a quiet magic trick, performed in plain sight. For a long time, the explanations seemed reasonable. Perhaps it was a kind of glue, but geckos leave no sticky trace. Perhaps it was suction, a popular idea for much of the 20th century. Early microscope images even seemed to show tiny structures that looked like suction cups. But the idea did not hold. Geckos stick perfectly well in a vacuum, where suction cannot work. They stick to surfaces far too rough for a seal. The truth, as it often is, was stranger and more elegant. The secret to the gecko's grip is not a biological trick in the way we normally think. It is not a special chemical or a mechanical hook. The force that holds a gecko to a ceiling comes from the very fabric of reality itself. It arises from the quiet, constant dance of particles in what looks like empty space. It is a quantum effect. Understanding this has not only solved an ancient mystery but has opened the door to a world of new technology. To understand it, we need to take a journey that begins with the visible world of the gecko's foot, and ends in the shimmering, unseen realm of the quantum vacuum. A universe on a toe. To begin, we have to appreciate the architecture of the gecko's foot. It is a masterpiece of natural engineering, refined over millions of years. Genetic analysis suggests this solution was so effective that it evolved independently at least 11 different times. When you look at a gecko's foot, you see broad pads at the end of its toes. These pads are covered in visible ridges, running crosswise like tire treads. These are called lamellae. For a long time, this was as far as our understanding went. The real story begins when we look closer. When powerful microscopes were first aimed at these lamellae, scientists saw they were not smooth at all. They were covered in a dense forest of microscopic hairs. These structures are called setae. They are not soft like our own hair, but are made of a stiff protein called beta-carotene, the same material in reptile scales. And they are packed with an almost unbelievable density. A single tokay gecko can have around 14,000 of these setae on every square millimeter of its toe pads. Each one is about the thickness of a human hair. This discovery was a monumental leap. In the 1960s, scientists were able to see this microscopic forest for the first time. They initially, and incorrectly, thought the ends were the tiny suction cups we had already ruled out. The structure was so fine, it was easy to misinterpret. But the existence of these hairs suggested a new idea: surface area. By having millions of these tiny fibers, the gecko was dramatically increasing how much of its foot was in contact with the surface. But friction alone was not enough to explain the strength of the grip. The final piece of the biological puzzle did not appear until the electron microscope allowed us to zoom in even further. What we found there was mind-boggling. The tip of every single seta branches out again, splitting into hundreds, sometimes even 1,000, of even tinier, nanoscale projections. These are called spatulae. They look like tiny, triangular tips at the very end of the line, each one only about 200 nanometers wide, smaller than the wavelength of visible light. Let's do some quiet, staggering math. A single gecko has roughly 6.5 million setae on its feet in total. If each of those has, on average, a few hundred spatulae at its tip, that means a gecko brings over 1 billion tiny, nanoscopic pads into contact with a surface every time it takes a step. This phenomenal hierarchy, from lamellae to setae to spatulae, allows the gecko's foot to become an almost perfect contact machine, conforming to any surface, no matter how rough or smooth. It can touch the microscopic peaks and valleys present on every object. But this still does not answer the most important question. We know the gecko can get incredibly close to a surface on a massive scale. But what is the force? What is the invisible glue that takes over at that infinitesimal distance? For that answer, we have to leave the world of biology and enter the world of fundamental physics. The physics of the stick. For a long time, the nature of this adhesive force was debated. We had ruled out suction and simple friction. Capillary action, the force that makes water climb a narrow tube, was another candidate. Perhaps a microscopic layer of water was creating surface tension. However, research in the early 2000s, led by biologists like Keller-Autumn, dismantled this idea. They showed that geckos stick just as well, if not better, to surfaces that repel water. If water were the key, you would expect the opposite. So, it was not suction, not glue, not Velcro, and not water. What was left? The answer had to be something more fundamental, a force that operates between any two objects that get close enough. The answer, as Keller-Autumn's team demonstrated, is a subtle and pervasive force known as the van der Waals force. This force is named after the Dutch scientist Johannes Diederik van der Waals, who proposed it in 1873. Unlike strong chemical bonds, van der Waals forces are much weaker. They are a gentle, fleeting attraction between separate, uncharged atoms. In our everyday world, we do not notice them. But when you have billions of points of contact, as a gecko does, these whisper-thin forces sum up to something powerful. To understand this, we need to break down what the van der Waals force is. It is a family of interactions, but the most important one for the gecko is the London dispersion force. This is the true quantum trick. It exists between all atoms and molecules, even perfectly neutral, nonpolar ones. And the reason for its existence is rooted in the probabilistic nature of the quantum world. Picture a neutral atom. It has a positive nucleus and a cloud of negative electrons buzzing around it. Quantum mechanics tells us that we can't know the exact position of an electron at any given moment. The electron cloud is a cloud of probability. At any single instant, the electrons are not going to be perfectly distributed. For a fleeting moment, there might be slightly more of the electron cloud on one side of the atom than the other. In that instant, the neutral atom becomes a temporary, lopsided, instantaneous dipole. Now, imagine this atom is next to another neutral atom. That fleeting dipole in the first atom will influence its neighbor, inducing a corresponding, synchronized dipole in the second atom. For that one flickering moment, the two atoms are attracted to each other. The next moment, the electron clouds shift, and the dipoles vanish or reappear, but the fleeting attraction happens again, and again, and again. It is a constant, quiet, synchronized dance of fluctuating charges. This London dispersion force is incredibly weak, and it only works over incredibly short distances, typically less than a nanometer. Our fingers are like a mountain range. We cannot get enough of our atoms close enough to a wall to feel this force. But the gecko can. This is where the story comes together. The entire, elaborate structure of the gecko's foot is an evolutionary marvel designed to solve one problem: getting as many atoms as possible as close as possible to the atoms of a surface. When a gecko places its foot, those billions of spatulae drape over the surface, and this quantum whisper kicks in. Each spatula provides a minuscule force, but when you multiply that tiny force by the billions of contact points, the collective strength becomes enormous, strong enough to support the gecko's entire body weight and more. Calculations show that if a gecko could engage all its setae at once, it could theoretically support about 130 kilograms. The genius of the system does not stop there. The gecko controls this force mechanically. To stick, it curls its toes, pushing the setae at a specific angle. To unstick, it doesn't pull straight up. Instead, it peels its toes away, changing the angle of the setae. By increasing the angle to about 30 degrees, the adhesive force drops to nearly zero, and the foot releases effortlessly. This allows the gecko to attach and detach its feet in milliseconds, letting it run across a ceiling. So the secret is not glue, it is quantum mechanics. Every step a gecko takes is a masterclass in applied physics, harnessing a fundamental force of the universe born from the very uncertainty of existence. The deeper magic: we have established that the gecko sticks because of the London dispersion force. But there is another way to look at this, a way that frames the force not as coming from the particles themselves, but from the empty space between them. To go down this final rabbit hole, we need to talk about one of the most bizarre concepts in modern physics, the Casimir effect. First, we have to change our idea of empty space. A perfect vacuum is not empty. The quantum vacuum, as it's called, is a seething soup of energy. Due to the same Heisenberg Uncertainty Principle, this vacuum is filled with virtual particles that pop into existence from nothing, exist for an impossibly short time, and then annihilate each other. This is happening everywhere, all the time. In 1948, the Dutch physicist Hendrik Casimir had a thought experiment. Imagine two perfectly flat, uncharged metal plates in a vacuum, placed incredibly close to each other. Classical physics says nothing should happen, but Casimir predicted something else. He realized that the empty space outside the plates was different from the empty space between them. Outside the plates, virtual particles of all possible wavelengths can exist. But in the tiny gap between the plates, only virtual particles whose wavelengths fit perfectly into that gap are allowed. This means there are more virtual particles pushing on the asterisk outside of the plates than there are on the asterisk inside. The pressure of the quantum vacuum from the outside is greater. The result is that the two plates are pushed together by an invisible force that comes from the structure of the vacuum itself. This is the Casimir effect. For decades it was theory, but in 1997, it was measured directly. Nothing, it turns out, exerts a force. What does this have to do with the gecko? The connection is profound. The London dispersion force is now understood as being deeply connected to the Casimir effect, sometimes described by a variation known as the Casimir-Polder force. They are two sides of the same quantum coin, both springing from the same fundamental source, the energy of the quantum vacuum. So when a gecko presses its billions of spatulae against a wall, it is, in a literal sense, harnessing the energy of empty space. It is creating countless tiny regions where the pressure of the quantum vacuum is reduced, allowing the greater pressure of the vacuum everywhere else to press its feet against the surface. The gecko isn't just sticking to the wall, it is being pushed against the wall by the very fabric of spacetime. It is a trick that evolution stumbled upon millions of years ago, a trick we are only now beginning to copy. The human connection. Nature figured this out long ago. For us, the discovery that the gecko's stickiness is based on a universal physical principle was a game changer. It meant we could, in theory, replicate it. This kicked off a race in biomimicry, the field of looking to nature for engineering solutions. The prize: a synthetic, reusable, super strong adhesive with no sticky residue. Gecko tape. One of the early pioneers was André Geim, who would later win a Nobel Prize for discovering graphene. In the early 2000s, his team created one of the first prototypes, famously using a small patch to stick a Spider-Man toy to a ceiling. It was a playful but powerful demonstration. Since then, the field has exploded. But replicating the gecko's system is not easy. There are immense challenges. The first is manufacturing at a nanoscale. The second, and perhaps biggest, is the dirt problem. A real gecko's foot is self-cleaning. The mechanics of how the spatulae attach and detach seems to shed dirt particles. Our synthetic versions tend to get clogged. Despite these hurdles, the progress has been astonishing. One of the most exciting areas is robotics. NASA has been a major driver, developing gecko grippers for use in space. Because the adhesion relies on van der Waals forces, it works perfectly in a vacuum. These grippers have been tested on the International Space Station, with the ultimate goal of using them to grapple with and clean up orbital debris. A robot could simply touch a piece of tumbling junk to capture it. Here on Earth, the applications are just as revolutionary. In manufacturing, gecko grippers can handle delicate materials like glass without leaving residue. In 2024, researchers developed an advanced adhesive that mimics the soft and rigid tissues in a gecko's foot, allowing it to grip uneven surfaces more effectively. There are concepts for search and rescue robots that could climb over rubble in disaster sites. Perhaps the most profound impact will be in medicine. For decades, we have closed wounds with sutures or glues, which can be invasive or cause inflammation. Now, researchers are developing biocompatible gecko-inspired adhesives. Imagine a sterile bandage placed over an internal incision during surgery, sticking firmly in the wet environment of the body, and then simply dissolving away as the tissue heals. This could change how we approach surgery and wound care. This journey, from a lizard on a wall, down to the nanoscale hairs on its feet, and all the way into the frothing energy of the quantum vacuum, shows how a simple question can unlock a universe of knowledge. We have seen how a biological mystery became a puzzle of physics, and how solving it is leading to a future of wall-climbing robots and new medical treatments. The story of the gecko's foot is a powerful reminder of the deep connections that bind the universe together. It shows that the line between biology and physics is blurry, and that some of nature's most elegant solutions are built upon the strangest rules of reality. It started with Aristotle's observation of a lizard on a tree, and has led us to the edge of quantum field theory. It leaves you to wonder, what other profound secrets are hiding right in front of our eyes, waiting for us to look a little closer? If this exploration into the quiet science of the world around us helped you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share a thought about where you're watching or listening from. Why the emptiest thing is also the heaviest. It begins with a quiet question, a riddle that seems to float in the space between stars. What is the emptiest thing we can imagine, that is also the heaviest thing in the entire universe? So heavy, in fact, that it is gently pushing everything apart. The answer is not a star, or a planet, or even a black hole. The answer is nothing. The vacuum, the stillness of perfect, empty space. This is a journey into that idea. It is not a story of sudden shocks, but of slow, unfolding discoveries that gradually changed our picture of reality. We will follow the quiet thoughts of scientists who looked at the universe and saw something that wasn't supposed to be there. We will see how one of science's most famous equations, E equals mc squared, revealed that the vacuum of space is not a void, but is filled with a hidden energy. An energy that has, over billions of years, grown to become the single most dominant force in the cosmos, shaping the final destiny of our universe. The story of nothing, it turns out, is the story of everything. To begin, we have to travel back to a time when nothing was a much simpler idea. For most of history, the concept of a true, perfect void was a philosophical question more than a scientific one. The ancient Greeks were divided. Some, like Parmenides, argued that a true vacuum was impossible. Nature, he felt, would not allow it. If you can speak of it, it must be something. Others, like Democritus, imagined that all of reality was made of tiny atoms moving through an endless, empty space, the void. Without that emptiness, they reasoned, motion itself could not happen. This question remained for centuries. As science began to take shape, the idea of a true void fell away. In the 17th century, trying to understand how light could travel through the emptiness of space, scientists revived an old idea, the luminiferous ether. They imagined this ether as an invisible substance that filled all of space. It had no color, no smell, no mass, but it was thought to be just rigid enough to carry waves of light from the stars to us, much like sound moves through air. Space was not empty, it was filled with this silent, unseen medium. This was the accepted view for more than 200 years. The universe was full. But in 1887, two American scientists, Albert Michelson and Edward Morley, designed an experiment to finally prove it existed. Their idea was beautifully simple. If the Earth is moving through a still ocean of ether, then the speed of light measured in the direction of our movement should be slightly different from the speed of light measured at an angle to it. It's like swimming in a river. Your speed changes if you swim with, against, or across the current. They built a delicate instrument, an interferometer, able to detect the smallest change in light speed. They took their measurements, and they found nothing. No difference at all. They rotated their machine and tried again. Still nothing. The speed of light refused to change. The Michelson-Morley experiment became known as the most successful failure in the history of science. Its inability to find the ether was a quiet, definitive turning point. The conclusion, though strange, was unavoidable. The luminiferous ether was not there. And so, as the 20th century began, the idea of emptiness returned. The void had won. Space was, after all, truly and deeply empty. If you could build a box, remove every particle of air, and shield it from all light and radiation, you would have a box of perfect nothing. It would weigh nothing and it would do nothing. This was the clean, classical picture of the vacuum. But this quiet image was about to be unsettled, first by a gentle tremor, and then by a deep, quantum shift in understanding. The first major clue on this journey does not come from someone studying emptiness, but from someone trying to understand everything else. His name was Albert Einstein, and in 1915 he offered the world his theory of general relativity, a new way of seeing space, time, and gravity. Before Einstein, space was seen as a passive backdrop, an empty stage. But Einstein revealed something different. Space and time are woven together into a single fabric called spacetime. And this fabric is not passive, it is a physical thing. It can bend and stretch and warp in the presence of matter and energy. Gravity, Einstein showed, is not a force pulling things across space. It is the shape of spacetime itself. The Earth orbits the Sun not because of a mysterious pull, but because it is following the straightest possible path through the deep curve in spacetime created by the Sun's mass. Space was no longer an empty container. It was a physical entity. The story deepens with another of Einstein's ideas, perhaps the most famous equation in science, E=mc². It is a simple formula, but its meaning is profound. It tells us that energy and mass are two aspects of the same thing. They can be converted into one another. Mass is a form of concentrated energy. And energy, even without mass, has a gravitational effect. It curves spacetime. Even light, which has no mass, has its path bent by gravity because its energy warps the fabric of space. It was in the overlap of these two ideas, dynamic spacetime and the equivalence of mass and energy, that Einstein found the first hint that nothing might be something. When he first wrote his equations for general relativity, he found they described a universe that should be unstable. Gravity, being always attractive, should cause all the matter in the universe to eventually collapse on itself. At the time, the common view was that the universe was eternal and static. To balance his equations and produce the still universe everyone expected, Einstein added what he later called a fudge factor. He introduced a small term, a kind of gentle, anti-gravity push that would come from space itself, counteracting gravity's inward pull. He called it the cosmological constant. This constant suggested that even a perfect vacuum, empty of all matter, would have a hidden energy built into the fabric of space. But then, in 1929, the astronomer Edwin Hubble made a quiet, landmark discovery. He observed that distant galaxies were all moving away from us. And the farther away they were, the faster they were receding. The universe wasn't static, it was expanding. The need for a balancing act was gone. Einstein later called the cosmological constant the biggest blunder of his life. He had introduced it only to keep the universe still, and the universe was not still. He had missed the chance to predict the expansion himself. He set the idea aside, and for many years, most physicists agreed. The cosmological constant was a mistake. The vacuum was back to being just empty. But perhaps he was too quick to dismiss his blunder. Perhaps he had accidentally uncovered a deep truth about the nature of emptiness, only to let it fall away, waiting for another, stranger idea in physics to reveal its true importance. At the same time Einstein was rethinking the very large, a new generation of scientists was exploring the strange and quiet world of the very small. This was the quantum revolution, and it would transform our idea of nothing from a simple void into a place of constant, subtle motion. At the heart of quantum mechanics is a rule that gently unravels our everyday intuition, the Heisenberg Uncertainty Principle. In simple terms, it says there are limits to what we can know about a particle at any given moment. The more precisely you know its position, the less precisely you can know its momentum, and vice versa. This is not a limit of our tools, it is a fundamental blurriness in the nature of reality itself. A quieter, but equally profound, version of this principle relates energy and time. It says that for very short moments, the law of energy conservation can seem to be flexible. Energy can be borrowed from the vacuum, as long as it is returned almost instantly. This idea changes everything when paired with quantum field theory. According to this theory, the most fundamental things in the universe are not particles, but fields. There is an invisible field for every particle: an electron field, a photon field, a Higgs field. These fields exist everywhere in space and time. What we see as a particle is just a small, localized vibration, a ripple, in its field. So, let's return to our box of nothing. In classical physics, it is empty. But in quantum field theory, that empty box is still filled with all of these fundamental fields in their lowest possible energy state. This state is called the ground state, or the vacuum state. And here is the crucial, quiet point. The energy of this ground state is not zero. A quantum field can never be perfectly still, with an energy of exactly zero. To do so would violate the uncertainty principle. So even in its calmest state, every field retains a minimum amount of energy. This is known as zero-point energy. It is the quiet, residual hum of the universe. This means that empty space is never truly empty. It is a landscape of subtle, constant fluctuation. For fleeting moments, these fluctuations can borrow enough energy from the vacuum to create a particle and its antiparticle. These virtual particles appear from nothing, exist for a moment too brief to be measured directly, and then vanish, returning their borrowed energy. This isn't just a story. It means that every cubic centimeter of so-called empty space is actually a soft, bubbling foam of these phantom particles, winking in and out of existence. The vacuum is a quiet sea of potential. The emptiest place we can imagine is, at its most fundamental level, alive with a subtle, endless activity. Our old, serene picture of the void is gone, replaced by the quantum vacuum. A place filled with energy and the gentle dance of virtual matter. This idea of a humming, energetic vacuum might sound like a mathematical fiction. It is so different from our experience that it is natural to be skeptical. Is there any physical evidence that this vacuum energy is real? The first piece of hard evidence comes from something called the Casimir effect. Predicted by the Dutch physicist Hendrik Casimir in 1948, the experiment is beautifully simple in concept. Imagine taking two perfectly smooth, uncharged metal plates and placing them extremely close together in a vacuum, just nanometers apart. Classically, nothing should happen. But the quantum vacuum is filled with virtual particles of all wavelengths. Outside the plates, virtual photons of all possible wavelengths can exist. But the tiny space between the plates acts like a resonant cavity. Only virtual photons whose wavelengths fit neatly into that gap are allowed. This means many of the longer wavelength virtual particles are excluded. The result is a subtle imbalance. There are more quantum fluctuations, more virtual particles, pushing on the outside of the plates than on the inside. This creates a tiny, attractive force, pushing the plates together. This is the Casimir force. And it is not just a theory. In 1997, it was measured, and the results perfectly matched the predictions. Scientists have measured the force exerted by empty space. A second piece of evidence is even more subtle, found deep inside an atom. It is called the Lamb shift. According to early quantum theory, certain electron orbitals in a hydrogen atom should have exactly the same energy. But in 1947, Willis Lamb discovered this wasn't true. He found a tiny, almost imperceptible difference in energy between two of these states. The reason, again, lies in the quiet energy of the vacuum. The electron is not moving through a simple void. It is moving through that sea of virtual particles. The constant interaction between the electron and the vacuum's fluctuations slightly shifts its energy level in a way that can be calculated and measured with incredible precision. The Casimir effect and the Lamb shift are quiet confirmations. They elevate the idea of vacuum energy from a strange theory to an experimental fact. Emptiness is not a void. It is a physical thing, with measurable energy. And this leads to the next question. If this energy is real, does it have weight? And if it does, how heavy is nothing? We have seen that empty space is filled with a baseline energy. Now we must return to Einstein and his equation, E equals mc squared, to understand what this means on a cosmic scale. The equation tells us that energy is equivalent to mass. Therefore, the energy humming in the vacuum must have mass. It must have weight. The energy of empty space must exert a gravitational pull, just like everything else in the universe. So, how much does the vacuum weigh? Cosmologists have been able to measure the density of this vacuum energy by observing the expansion of the universe. The value they found is almost impossibly small, approximately 5.96 by 10 joules per cubic meter. If you convert that to its mass equivalent, it comes out to less than 10 squared to the power of 6 kilograms per cubic meter. That's like a few hydrogen atoms in a space the size of a large room. At first, this seems completely insignificant. How could something so thin, so close to nothing, be the heaviest thing in the universe? This is where our intuition gently fails us. To understand, we need to see how vacuum energy behaves compared to normal matter as the universe expands. Imagine a box filled with normal matter. If you double the size of the box, the matter inside spreads out. Its density is cut in half. The same is true for light. As the universe expands, its energy dilutes. But vacuum energy is different. It is not made of particles that can be spread thin. It is an asterisk intrinsic property of space itself. The amount of energy is proportional to the volume of space. This leads to a quiet but staggering conclusion. If you take your box of nothing and double its size, you now have twice as much vacuum energy. The density stays the same because you have simply made more space, and every bit of space has its own inherent energy. Everything else in the universe, stars, gas, dust, dark matter, gets thinned out as the universe expands. Its influence becomes weaker over time. But vacuum energy does the opposite. As the universe gets bigger, the total amount of vacuum energy gets bigger, and its relative contribution to the universe's total energy grows. It is playing a long, quiet game. Our story is nearing its end. We know the vacuum has energy, that this energy has weight, and that its total amount grows as space expands. Now, we must connect this to the discovery that this energy is pushing the universe apart. After Hubble discovered the expanding universe in 1929, the great question was about its future. Gravity pulls things together, so everyone assumed that the mutual pull of all the galaxies must be acting as a brake on the expansion. It had to be slowing down. For decades, astronomers tried to measure this deceleration. Then, in 1998, two separate teams of astronomers were using a special kind of exploding star, a type Ia supernova, to map the history of the expansion. They are useful because they are all thought to explode with the same brightness. By measuring how dim they appear, you can calculate how far away they are. Both teams expected to find that the expansion was slowing. Instead, they found the exact opposite. The distant supernovae were dimmer, and therefore farther away, than they should have been. This meant that the expansion of the universe is not slowing down. It's accelerating. This discovery was so profound it earned the team's leaders the Nobel Prize in Physics in 2011. Something was overpowering the gravity of all the matter in the cosmos and pushing spacetime apart. This mysterious influence was given a fitting name: dark energy. Suddenly, physicists remembered Einstein's biggest blunder: the cosmological constant. When you look at vacuum energy through the lens of general relativity, a strange property emerges. In Einstein's theory, pressure also contributes to gravity. And the vacuum energy predicted by quantum theory has a strong negative pressure. You can think of it like the tension in a stretched rubber band. it pulls inward. But in general relativity, a large negative pressure has a strange gravitational effect. It creates a repulsive force. It is a perfect anti-gravity. The properties of this vacuum energy match the properties of dark energy perfectly. Einstein's blunder was actually a prediction, decades ahead of its time. And this brings us back to our riddle. Why is the emptiest thing also the heaviest? In the early universe, the density of matter was much higher, and its attractive gravity was dominant. But as the universe expanded, the density of matter thinned out, while the density of vacuum energy remained constant. Around 6 billion years ago, a quiet tipping point was reached. The total repulsive push from the ever-growing amount of vacuum energy finally became stronger than the weakening pull of all the matter. The cosmic brakes became a cosmic accelerator. Today, when we measure the total mass energy of the universe, the results are humbling. The ordinary matter that makes up every star, planet, and person accounts for less than 5%. Dark matter, an unseen substance we only detect through its gravity, makes up about 27%. And the rest, roughly 68%, is dark energy, the energy of nothing. The emptiest thing we can imagine outweighs everything else combined. It is, by far, the heaviest and most dominant component of our cosmos. If this kind of calm exploration into the quiet mysteries of the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Now, as compelling as this story is, our work is not quite finished. There is a final twist, a detail that doesn't fit. In the case of vacuum energy, it is not a small detail. It is the single largest disagreement between theory and observation in the history of physics. It is called the cosmological constant problem. Here is the issue. We have measured the density of dark energy through our cosmological observations. It's tiny, but it's there. However, when physicists try to calculate what the energy of the vacuum should be, based on quantum field theory, they get an answer that is catastrophically wrong. The theoretical prediction for the energy density of the vacuum is about 10 to the power of 120 times larger than the value we actually observe. It is a number so large it's difficult to comprehend. If the vacuum energy were truly that strong, its repulsive force would have torn the universe apart in the first moments after the Big Bang. No atoms could have formed, no stars, no galaxies, no life. So why is there this profound disagreement? The honest answer is that nobody knows. It is the deepest puzzle in modern physics. It is as if our two best theories of the universe, general relativity for the very large, and quantum mechanics for the very small, are speaking different languages when they try to describe this one crucial value. Many solutions have been proposed. Perhaps some unknown principle of nature causes nearly all of this energy to cancel itself out, leaving only the tiny remnant we see. Or perhaps our understanding is incomplete. Recent observations from projects like the Dark Energy Survey are still refining our measurements, confirming that dark energy appears constant, but also deepening small tensions with our standard model. This is a field of quiet, active research. The final chapter of this story is not yet written. We began with a riddle. What is the emptiest thing that is also the heaviest? The answer, we have seen, is the vacuum. We have seen that empty space is not a void, but a place of quiet complexity, filled with the fundamental fields of nature humming with a subtle, constant energy. It is a quantum foam, alive with the fleeting presence of virtual particles. We saw how E=mc² provides the bridge, telling us that this quiet energy has weight, and that it shapes spacetime. And finally, we saw how this weight doesn't pull, but pushes. Its strange negative pressure creates a repulsive force that has taken control of the cosmos, accelerating its expansion. The story of nothing is the story of the universe's past, its present, and its future. The energy of the void is currently the heaviest thing there is, and its properties will likely determine the ultimate fate of the cosmos. A slow, endless expansion into a cold, dark, and truly empty future. So the next time you look up at the night sky, at the vast, dark emptiness between the stars, remember what you are truly seeing. You are not looking at nothing. You are looking at the most mysterious, the most powerful, and the most massive thing in the entire universe, hiding in plain sight. The secret energy hidden in pure nothingness. We believe we know what empty space is. A silent, peaceful void. We've been taught that nothing is the absence of everything. The blackness between the stars, or the perfect stillness inside a chamber from which all air has been removed. And yet, this picture, as natural as it feels, might be one of the most profound misunderstandings in all of science. In reality, the nothingness all around us, the space between you and this screen, the vast interstellar voids, may be one of the most active and energetic places we know. Hiding in every part of that supposed emptiness is a quiet energy, so fundamental it could be the force that dictates the fate of everything. This is not a story from fiction. It is the story of an energy hidden in pure nothingness, a ghostly force that has been proven to exist, and a cosmic mystery so deep it has been called the single greatest problem in physics. By the end of this journey, you may not look at empty space the same way again. You may begin to see it not as an absence but as a presence. A quiet, simmering foundation of reality that is shaping our entire cosmos. The classical void, an intuitive idea. Let's begin with an idea that feels completely natural, something we all understand. The idea of emptiness. Imagine an empty room. You can walk around in it, wave your hands through the air. Now, let's imagine we use a powerful pump to draw all of the air out. The room is now a vacuum. There are no more nitrogen or oxygen atoms. There is no dust, no stray microbes. It is silent. It is still. If we could make this vacuum perfect, we could remove every last particle. We could shield it from all outside light. And to be thorough, we could cool the entire chamber down to the lowest possible temperature in the universe. Absolute zero. Minus 273.15 degrees Celsius. At this temperature, all heat, all motion, should stop. What are we left with? According to the physics we've known for most of history, what we call classical physics, we are left with perfect, absolute nothingness. A void. It has zero energy, zero particles, zero temperature. It is a state of complete tranquility. For centuries, this was the bedrock assumption. The ancient Greeks debated if a perfect void could even exist, with some arguing that nature would always rush in to fill any emptiness. But as science progressed, we learned to create vacuums. We used them to build the first electronics, and we looked out into space and saw what appeared to be the ultimate vacuum, stretching for light years between the stars. The idea of a perfect void became a scientific baseline. It was a true zero. A blank canvas on which the universe of matter and energy performed. This classical vacuum is simple, clean, and it makes sense to our everyday experience. If you remove everything from a space, what you have left is nothing. It has no properties, no features, and certainly no energy. This intuitive, comfortable idea of nothingness is, in many ways, the foundation of a common-sense worldview. It is also fundamentally incomplete. It is the logical, elegant idea we must first understand before we can appreciate the quiet truth. Because at the turn of the 20th century, two revolutions in physics arrived, and they began to reveal something unimaginably strange and active lurking underneath. The quantum reality, a new set of rules. So, how did our peaceful, empty void become a quiet sea of energy? The end of classical nothingness began with the birth of quantum mechanics, a new and unfamiliar set of rules that govern the universe at its most fundamental level. And one of its central ideas delivered a fatal blow to the concept of perfect stillness. That idea is the Heisenberg Uncertainty Principle. Proposed by Werner Heisenberg in 1927, the uncertainty principle is a cornerstone of the quantum world. In simple terms, it states that there is a fundamental limit to how well you can know certain pairs of properties at the same time. For example, the more precisely you measure a particle's position, the less precisely you can know its momentum. This isn't a failure of our tools. It's not because our instruments are unsteady. The principle states that this uncertainty is an intrinsic feature of reality itself. A particle doesn't always have a single, definite position and a single, definite momentum. It exists in a cloud of possibilities. The uncertainty principle also applies to the relationship between energy and time. It dictates that you cannot know the exact energy of a system over an incredibly short period. There is always a fundamental quantum fuzziness. Think about what this means for our perfect vacuum. A state of absolute nothingness, with precisely zero energy, would violate this principle. If the energy of the vacuum were exactly zero, and stayed zero, you would know its value and its rate of change with perfect certainty. Quantum mechanics suggests the universe simply does not allow for a state of such absolute stillness. So if the energy of the vacuum can't be perfectly zero, what must it be? It must be fluctuating. It must be simmering with some minimal, baseline level of energy that can never be removed. This idea was formalized with the development of quantum field theory, or QFT. In QFT, the most fundamental components of the universe are not particles. They are fields. Imagine the universe is filled with invisible, all-pervading fields, an electron field, a photon field, and so on for every particle we know. What we perceive as a particle, like an electron, is simply a localized vibration, a ripple in its corresponding field. Think of a calm lake. The lake itself is the field. If you tap the water's surface, you create a ripple. That ripple is the particle. This is the new picture of reality. The universe isn't a collection of tiny objects moving through an empty void. The universe is a collection of fundamental fields. And an empty vacuum is no longer a space devoid of things. It is the state where all of these quantum fields are in their lowest possible energy state, their ground state. But as the uncertainty principle demands, that ground state cannot be perfectly, absolutely zero. The hum of the void, zero-point energy. This brings us to the heart of the matter. If every quantum field that fills the universe can never be perfectly still, it means that even in a perfect vacuum, at absolute zero, these fields are constantly humming with a minimum, non-zero amount of energy. This irreducible, fundamental energy of the vacuum is known as zero-point energy. Think of a guitar string. It has a fundamental note, its lowest possible vibration. You can pluck it to play louder or higher notes, but it can never be more still than its resting state. The zero-point energy is like the resting tension of that string, but for the universe itself. Every point in space is filled with these quantum fields, all vibrating quietly. This is the secret energy, hidden in pure nothingness. It is not energy from matter or heat or light. It is the energy that space itself possesses simply because it exists and obeys the laws of quantum mechanics. It is the background hum of the cosmos. So, what does this energy do? This is where the idea gets even stranger. According to quantum field theory, these ceaseless fluctuations can, for incredibly brief moments, give rise to particles. The energy-time uncertainty principle implies that the universe allows for tiny, temporary energy loans from the vacuum, as long as they are paid back very, very quickly. A fluctuation in a field can momentarily spike, creating a particle and its antimatter counterpart out of thin air, for instance, an electron and a positron. These are not the stable, long-lived particles that make up you and me. They are called virtual particles. They are ghost-like entities, emerging from the void, existing for a time so short we can never hope to directly capture one, and then annihilating each other, vanishing back into the energy from which they came. This is happening right now, all around you. In the space between your eyes and this screen. In the vast, dark voids between galaxies. Every part of the universe is a quiet, effervescent cauldron of these virtual particles. A quantum foam of transient existence. The vacuum, the perfect nothingness we imagined, is in fact a place of constant, hidden activity. Our tangible, stable world of matter is just the long-lasting froth sitting atop this deep, simmering quantum ocean. This sounds like a strange fiction. How could we possibly know if it is real? For a long time, it was thought to be a purely theoretical idea. But then, a Dutch physicist named Hendrik Casimir proposed an experiment that would allow us to feel the force of nothingness. Touching the ghost, the Casimir effect. By the middle of the 20th century, the idea of zero-point energy and virtual particles was a well-established prediction, but it remained just that, a prediction. It was like trying to weigh a shadow. This all changed in 1948, when Hendrik Casimir proposed a brilliant and surprisingly simple thought experiment. Imagine you take two perfectly smooth, uncharged metal plates. You place them in a perfect vacuum, parallel to each other and incredibly close together, separated by less than a micron. According to classical physics, absolutely nothing should happen. The plates are uncharged. There is no air between them. They should just sit there, motionless. But Casimir, thinking about the quantum vacuum, predicted something extraordinary. He predicted that the two plates would be pushed together by an invisible force. A force generated by the pure nothingness of the vacuum itself. This is now known as the *Casimir effect. The explanation is as elegant as it is subtle. Remember that the quantum vacuum is filled with a soup of virtual particles of all possible wavelengths. Like an ocean with waves of every size. Outside the two plates, in the open vacuum, virtual particles of every possible wavelength can exist. The full, chaotic energy of the vacuum is present. But in the tiny gap between the plates, it's different. The plates act like walls. Only virtual particles with wavelengths that fit neatly into that gap can exist there. A long wavelength virtual particle is too big to form. The gap acts as a filter, excluding many of the possible vibrations. This creates a quiet imbalance. There are more kinds of virtual particles popping into existence on the outside surfaces of the plates than on their inside surfaces. This means there is more pressure from these particles pushing inward than there is pushing outward. The result is a net force, gently squeezing the plates together. And this is not just a theory. The Casimir force has been measured. By the latter half of the 20th century, experiments began to confirm Casimir's prediction. The force is incredibly small, but it is undeniably real. Nothingness can push things around. This was monumental proof that the energy of the vacuum is a real, physical phenomenon. And it is not the only trace it leaves. More recently, experiments have shown that even the properties of the stable particles that make up our world carry an imprint of the virtual particles in the quantum vacuum, further connecting the visible world to this invisible one. This was a triumph for our understanding of reality. But this triumph came with a shadow. Because when physicists tried to calculate exactly how much energy this vacuum should contain, they stumbled upon the single largest disagreement in the history of science. The cosmic disagreement, the worst prediction in physics. With the Casimir effect confirming that vacuum energy was real, the next step was to calculate its total amount. Quantum field theory was the most successful theory ever devised, making predictions accurate to an astonishing degree. So, physicists set to work. They added up the zero-point energies of all the known quantum fields. And they got a number. The number they calculated for the energy density of the vacuum was impossibly large. If you were to take all of the energy and all of the matter of the entire observable universe, every star, every galaxy, and fit it into a single cubic meter, the energy of the vacuum predicted by theory would still be incomprehensibly greater. According to Einstein's theory of general relativity, all energy has a gravitational effect. An energy density this enormous should have crushed the universe into a singularity moments after it began. Stars should not have formed. Galaxies should not exist. We should not be here. Our very existence is the clearest proof that this calculation is wrong. This colossal mismatch is known as the cosmological constant problem. It is, without exaggeration, the largest discrepancy between theory and observation in all of science. Our best theory of reality makes a prediction for the energy of empty space that is wrong by about 120 orders of magnitude. That is a 1 with 120 zeros after it. A mistake of that scale is like measuring the width of a continent and being off by the diameter of the observable universe. It is so profoundly wrong that it tells us we are missing something absolutely fundamental about how reality works. For decades, many physicists hoped the answer was simple. Perhaps some unknown symmetry of nature forced all of these enormous energies to perfectly cancel each other out, leaving behind a perfectly empty, zero-energy void. But the universe, it turns out, is far more interesting than that. The answer isn't a catastrophically huge number, and it isn't zero either. The true energy of the vacuum is something else. It's tiny, it's subtle, and it is connected to the single biggest mystery in modern cosmology. The cosmic push, the shadow of dark energy. Our story now takes a leap, from the microscopic quantum realm to the grandest possible scale, the entire universe. For most of the 20th century, the prevailing wisdom was that the universe's expansion, started by the Big Bang, must be slowing down due to the gravitational pull of all the matter within it. Then, in 1998, everything changed. Two teams of astronomers were using distant supernovae to measure the expansion rate of the universe in the past. They found that the expansion isn't slowing down. It's speeding up. Something was gently pushing the universe apart, counteracting gravity. This mysterious, repulsive influence was given a fittingly enigmatic name: dark energy. Subsequent measurements have all confirmed its existence. Dark energy is real, and it is dominant, making up roughly 70% of the total energy in the universe. The matter that makes up you, me, and all the stars is less than 5%. We live in a universe run by something we cannot see and do not understand. So, what is this dark energy? Cosmologists found it has very particular properties. It appears to be a property of space itself. As space expands, more of this energy appears, keeping its density constant. It also exerts a negative pressure, which in general relativity creates a repulsive effect. A constant energy density, inherent to the fabric of space itself. Does that sound familiar? It is a perfect description of vacuum energy. Suddenly, the two biggest mysteries in physics seem to be two sides of the same coin. The zero-point energy predicted by quantum mechanics was the most natural candidate for the dark energy observed by astronomers. The secret energy of nothingness was the force driving the cosmos apart. It was a beautiful, unifying idea. And it revealed an even deeper problem. Astronomers could now measure the precise strength of dark energy. They could observe how fast the universe was accelerating and calculate the exact energy density required to produce that effect. And they found a number. The observed energy density of the vacuum is tiny, something on the order of 10 to the power of -10 joules per cubic meter. Now we can see the full, breathtaking scale of the paradox. Quantum theory predicts a vacuum energy that is 120 orders of magnitude larger than what our telescopes actually measure. The prediction isn't zero, and the observation isn't zero. They both agree that empty space has energy. But the theoretical value is astronomically larger than the real one. The energy is just small enough to have allowed galaxies and life to form over billions of years, and just large enough to begin gently pushing the universe apart now. This is the real cosmological constant problem. Why is there such a gargantuan chasm between what our most fundamental theory predicts and what our telescopes see? The unsolved mystery. Why is nothing so important? We are left looking into an abyss of our own understanding. We have two pillars of modern science. Quantum field theory, which describes the small-scale world with flawless precision, predicts a vacuum with an impossible amount of energy. General relativity, which describes the large-scale world of gravity, tells us through observation that this energy exists, but as a mere whisper of what it should be. The resolution, when it comes, will likely spark a revolution in our understanding of reality. So, what are the possibilities? One hope was a principle called supersymmetry, which proposed that every known particle has a heavier, superpartner. This would have created a perfect balance, with enormous positive and negative energy contributions canceling each other out to exactly zero. So far, however, experiments at the Large Hadron Collider have found no sign of these proposed partners. Another, more philosophical idea is the anthropic principle often paired with the concept of the multiverse. Perhaps, this thinking goes, there isn't just one universe, but a vast cosmic landscape of them. In most of these universes, the vacuum energy would be huge, and they would be sterile, collapsing instantly or being ripped apart. But by sheer chance, in a tiny fraction of them, the value would happen to be incredibly small. In these rare, life-friendly universes, beings like us could evolve to ponder the question. We find ourselves here for the simple reason that we couldn't exist to ask the question anywhere else. Or perhaps the answer lies in a new direction entirely, in a theory of everything that would finally unite the quantum world with gravity and explain how space-time behaves at its most fundamental level. Until we have that theory, this quiet mystery may remain unsolved. We started with the simple idea of nothing, a silent, empty void. We journeyed down into the fabric of reality itself and found that this nothingness is an illusion. The vacuum is not empty. It is a place of unimaginable energy, a quantum foam where ghostly particles flash in and out of existence, governed by the fundamental uncertainty of the cosmos. We learned that this energy leaves a tangible mark on our world, a tiny force that can be measured in a laboratory. And when we looked back out to the scale of the cosmos, we found that this same energy is now the dominant force in the universe, a dark energy pushing galaxies apart and driving the ultimate fate of reality. The great paradox is that the force that will determine the destiny of everything comes from the very emptiness we ignore every day. And it remains one of the deepest, most humbling mysteries we have ever encountered. What are your thoughts on this quiet mystery? Is the discrepancy a sign that our theories are incomplete? Or is it a hint that we live in a vast multiverse, in one of the few places where the cosmic conditions allowed life to begin? Feel free to share your thoughts in the comments below. And if this kind of exploration into the universe helps you wonder, consider liking the video and subscribing to the channel, so you don't miss our next journey into the beautiful, bewildering unknown. The invisible force tearing the universe apart. For what felt like a very long time, we thought we knew the story of our universe. It was a story written in the language of gravity. Born from the Big Bang nearly 14 billion years ago, the cosmos began a great expansion. But woven through every star and every galaxy was the steady, quiet pull of gravity. The force that gathered matter into the shapes we see today. Astronomers were sure of this story. Gravity was the main character. It shaped the beginning, the middle, and the end. Like a ball thrown into the air, the universe had been launched, and gravity was acting as a brake, slowing it down. The only real question left was a simple one. How would the story end? Would gravity's pull be strong enough to stop the expansion and reel everything back in, ending in a big crunch? Or was the expansion just fast enough to escape, slowing forever but never reversing, leading to a long, cold future called the Big Freeze? A crunch or a freeze? Those were the choices. It was a matter of weighing the universe to see which force would win. So, in the late 1990s, two teams of astronomers began the most careful cosmic search ever attempted. Using powerful telescopes on and off the Earth, they set out to look deep into the past. Their goal was straightforward: to measure exactly how much the universe's expansion was slowing down. They were not looking for something strange or unexpected. They were simply trying to read the last page of a book they thought they already understood. But what they found, in the faint light of distant dying stars, was not the end of the story. It was the beginning of a new and unsettling chapter. The data was clear, and it changed almost a century of thinking. The universe wasn't slowing down at all. It was speeding up. An invisible, unknown force is at work in the cosmos. It is overpowering gravity on the largest scales. And it is quietly, relentlessly, pulling the very fabric of the universe apart. To understand how strange this discovery was, we have to go back to the universe as we understood it at the start of the 20th century. Before the 1920s, the common view, even held by Albert Einstein, was that the universe was static. It was eternal and unchanging. It was a comforting picture. And it was completely wrong. The first clue came from an astronomer named Vesto Slipher. In the 1910s, he began studying the light from what were then called spiral nebulae. He used a technique that spreads light into its colors, like a rainbow. Within this spectrum are dark lines that act as fingerprints for chemical elements. Slipher noticed something odd. For most of these nebulae, the lines were shifted toward the red end of the spectrum. This is the phenomenon of redshift, and it is a cosmic version of the Doppler effect. When an ambulance siren moves away from you, its pitch drops. The sound waves are stretched. The same thing happens with light. If an object is moving away, its light waves are stretched, shifting them toward the longer, redder wavelengths. A redshift tells us something is moving away, and how fast. Slipher's work showed that almost every spiral nebula he looked at was moving away from us at incredible speeds. This was a profound clue, but it was Edwin Hubble who put the pieces together in the 1920s. First, he proved that these nebulae were not inside our own Milky Way. They were distant, island universes, galaxies in their own right. This discovery expanded the known universe by an unimaginable amount. But it was Hubble's second discovery, in 1929, that changed everything. By measuring both the distances to these galaxies and their redshifts, he found a simple relationship: the farther away a galaxy is, the faster it is moving away from us. This became known as Hubble's law, and it could only mean one thing: the entire universe is expanding. The best analogy is a loaf of raisin bread baking in an oven. The raisins are galaxies, and the dough is space itself. As the dough expands, every raisin moves away from every other raisin. A raisin close to you might move away an inch in a minute. A raisin twice as far away will move 2 inches in the same minute, because there's twice as much expanding dough in between. From any single raisin, all other raisins appear to be rushing away. This isn't an explosion in a pre-existing space. Space itself is stretching. This discovery was the proof for the Big Bang theory, the idea that the universe began in an incredibly hot, dense state and has been expanding ever since. And this brings us back to gravity. As soon as the expansion was established, the next thought was, what happens next? The universe is filled with matter. All of this matter has mass, and all mass exerts a gravitational pull. While the universe expands, gravity is constantly pulling back. It's a cosmic tug of war. For the next 70 years, cosmology was defined by this quiet battle. To figure out who would win, we needed to know how much matter was in the universe. We can call this value omega. If omega was greater than 1, gravity would eventually win, causing the big crunch. If omega was less than 1, gravity would lose, and the universe would expand forever into a big freeze. The mission of the 1990s was to settle this. It was to measure the history of the expansion, and to finally write the final chapter. To measure the history of the cosmos, you need a special kind of tool. You need a standard candle. The idea is simple. Imagine you see a single candle flame in a dark field. It's impossible to tell how far away it is. It could be a bright candle far away, or a dim candle close by. But if you have a special kind of candle that is always manufactured to have the same brightness, you can determine its distance just by seeing how dim it appears. In cosmology, finding a reliable standard candle is essential for measuring vast distances. For a long time, astronomers used stars called Cepheid variables. But to see across billions of years, they needed something far brighter. They needed an exploding star. Specifically, a Type Ia supernova. A Type Ia supernova is a very particular kind of explosion. The story begins with two stars orbiting each other. One of them has become a white dwarf, the super-dense corpse of a sun-like star. It is small, about the size of Earth, but incredibly heavy. A single teaspoon of its material would weigh several tons. This dead star is not alone. Its gravity begins to pull gas from its living companion star. For thousands or millions of years, the white dwarf gathers this material. As it feeds, its mass grows, and it approaches a quiet, unbreakable rule in physics, the Chandrasekhar limit. This limit is about 1.44 times the mass of our Sun. At this exact mass, the white dwarf becomes unstable. What happens next is almost instant and unbelievably violent. A wave of burning moves through the star. Within seconds, the entire white dwarf is consumed in an explosion that tears it apart. For a few weeks, this single exploding star can outshine its entire galaxy. And here is the important part. Because every Type Ia supernova is triggered by the same process, a white dwarf reaching the same mass, they all explode with almost exactly the same brightness. They are astonishingly reliable standard candles. Find a Type Ia supernova, measure how bright it appears, and you can calculate its distance. The light from that same supernova also gives us its redshift, which tells us how fast it is moving away. By the 1990s, technology had finally caught up with this idea. Two rival teams of scientists formed to undertake this search. One was the Supernova Cosmology Project. The other was the High-Z Supernova Search Team. They were competitors, but they shared the same goal: to find dozens of these explosions to measure the slowing of the cosmos. The expectation was clear. If the universe's expansion was slowing down, the most distant supernovae should appear brighter than expected. In a slowing universe, they wouldn't have traveled as far as you'd think. The light would be less dim. They were looking for overly bright supernovae. That was the signature of a universe being reined in by gravity. The year is 1998. For several years, the two teams had been in a frantic race, searching for faint smudges of light in distant galaxies. Slowly, they were building their cosmic map, plotting each supernova on a graph. On one axis was distance. On the other was redshift. All theories agreed on one thing. The data points should fall on the side of the graph that represented a slowing universe. Gravity demanded it. Saul Perlmutter's team, the Supernova Cosmology Project, gathered its data. As they analyzed the results, a deep sense of unease began to settle in. Something was wrong. The data points were not falling where they were supposed to. They weren't brighter than expected. They were dimmer. A dim supernova means it is farther away than its redshift would suggest. This was the exact opposite of what they were looking for. It was as if a car you thought was driving away at a constant speed was actually much farther away after an hour than you could possibly account for. The only way that could happen is if, at some point, the car had hit the accelerator. The team spent months convinced there must be an error. Could their calculations be wrong? Was there some unforeseen dust that made the supernovae look dimmer? They reran every analysis. They tried to find a mistake. But the result wouldn't go away. The supernovae were, without a doubt, dimmer than they should have been. Meanwhile, the High-Z team was independently reaching the same unsettling conclusion. Adam Rees, the lead analyst for the team, later described the moment he plotted their final data points. Instead of falling on the side of deceleration, they landed squarely on the side of the graph that represented acceleration. His reaction, he said, was not, "Eureka." It was, "Oh, dear." In early 1998, the two teams learned of each other's results. Any fear that one team had made a colossal error was replaced by a more profound shock. They had both found the same impossible thing. It wasn't dust. It wasn't an error. It was real. The universe's expansion is not slowing down. For the first several billion years after the Big Bang, it was slowing down, just as theory predicted. But then, around 5 to 6 billion years ago, something changed. A new, repulsive force began to dominate, and the expansion of the universe began to accelerate. The news landed like a quiet bombshell. It was as if we had thrown a ball into the air, watched it slow down, only to see it suddenly reverse course and shoot upwards, faster and faster. It broke the entire story of cosmology. This discovery would earn Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. They had set out to measure how the universe was slowing, and accidentally discovered it was being pulled apart. They had found the signature of a force that would come to be known by a simple, yet mysterious name, dark energy. This discovery rewrote our understanding of the cosmos, replacing a story we thought we knew with a quiet mystery. The questions this raises are some of the most profound in science. If you want to continue this journey into the biggest and most bewildering ideas shaping our view of reality, consider subscribing to the channel. It's the best way to make sure you don't miss our next exploration. Your support allows us to tackle these massive subjects, and we'd love to have you with us as we piece together the puzzle of the cosmos. Now, back to the mystery. What is this invisible force? So, our universe is being pushed apart by an invisible, repulsive force. What is it? The honest answer is, we don't know. But we have given our ignorance a name. We call it dark energy. The word dark here is used in the same sense as dark matter. It is dark to us because it is completely invisible and mysterious. We only know it exists because we can see its effect on the universe as a whole. And its effect is staggering. When we do the cosmic accounting, all the stars, galaxies, and planets make up less than 5% of the cosmos. Dark matter accounts for about 27%. The remaining 68%? That is dark energy. This means the dominant force shaping the fate of our universe is something we didn't even know existed until 1998. However, there is a prime suspect. And it is perhaps the strangest idea in modern physics. The leading candidate for dark energy is something called the energy of the vacuum. To understand this, we have to change our picture of empty space. We think of a vacuum as nothing. But one of the great lessons of quantum mechanics is that the vacuum is not empty. It is alive with what are called quantum fluctuations. For fleeting moments, pairs of virtual particles can spontaneously pop into existence from nothing, exist for an immeasurably short time, and then disappear back into nothingness. This isn't just a theory. Its effects are measurable. And according to Einstein's E=mc², if these virtual particles have energy, then the vacuum itself must have an intrinsic baseline level of energy. So what does this have to do with an accelerating universe? This is where we turn back to Albert Einstein's general theory of relativity. In 1917, Einstein found his equations predicted the universe must be either expanding or contracting. To match the belief that the universe was static, he added an extra term to his equations to counteract gravity. He called it the cosmological constant. It was a repulsive energy built into the fabric of space itself. When Hubble discovered the universe was expanding, Einstein discarded it, calling it his biggest blunder. But with the discovery of the accelerating expansion, Einstein's blunder has made a stunning comeback. A cosmological constant, a vacuum energy, has exactly the properties needed to explain what we observe. Here's the crucial part. As the universe expands, matter gets diluted. Its gravitational pull gets weaker. But vacuum energy behaves differently. It's a property of space itself. Its energy density, the amount of energy per cc, is constant. It never dilutes. So, as the universe expands and more space is created, you get more of this vacuum energy. According to general relativity, this constant energy density creates a negative pressure. A repulsive force. It acts like anti-gravity. This creates a quiet, runaway effect. The universe expands, which creates more space. More space means more vacuum energy. More vacuum energy creates a stronger repulsive push. That stronger push causes the universe to expand even faster. Once this energy starts to dominate over the ever-diluting pull of gravity, it takes over completely. This is the picture. The leading idea is that dark energy is the energy of the vacuum itself, Einstein's cosmological constant returned. It is the weight of nothingness, and it is pushing our universe toward its future. A discovery as reality-shattering as this cannot rest on a single piece of evidence. The scientific community needed confirmation from completely independent methods. In the years since 1998, that is exactly what we have found. The first major line of evidence comes from the very beginning of time, the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, a faint wash of microwave radiation that fills the entire sky. It is a snapshot of the universe when it was just 380,000 years old, a baby picture of the cosmos. Missions like the WMAP and Planck satellites have mapped this ancient light, showing tiny temperature fluctuations, the seeds of all future galaxies. By studying the asterisk size of these spots, we can measure the geometry of the universe. The CMB data is clear. To an incredibly high degree of precision, our universe is geometrically flat. This presents a problem. A flat universe requires a specific, critical density of matter and energy. But when we add up all the ordinary matter and all the dark matter, it only comes to about 30% of what's needed. Where is the other 70%? Dark energy provides the answer. The amount we infer from the supernova data, around 70%, is exactly what is needed to make the universe flat. The books are balanced. The second line of evidence comes from the way galaxies are scattered across the universe. It's called baryon acoustic oscillations, or BAO. It's a complicated name for an idea that acts as another cosmic ruler. In the early universe, gigantic sound waves rippled through the primordial soup. When the universe cooled, these waves were frozen in place, leaving an imprint on the distribution of matter. A preference for galaxies to be separated by a specific distance, about 500 million light-years. It's as if the Big Bang sent out a cosmic shout, and the echo is now imprinted in the sky. By measuring the apparent size of this standard ruler, at different times, surveys can map out the expansion history of the universe. The results are a stunning confirmation of the supernova data, showing a universe that was decelerating before an accelerating phase began. Finally, there is the evidence from the growth of cosmic structures. Gravity wants to pull matter together to make galaxy clusters bigger, while dark energy's push tries to slow that growth down. The rate at which these structures form is a direct probe of the strength of dark energy. The Dark Energy Survey, DES, after years of mapping the sky, released results in early 2026. By combining 4 different methods, it has produced some of the most precise constraints on cosmology to date. The results are a resounding confirmation of our standard model, known as lambda CDM. They pin down the amount of dark energy to be just under 70% of the universe. Across all of these independent methods, exploding stars, the afterglow of the Big Bang, the distribution of galaxies, and the growth of structures, the story is the same. An invisible force is accelerating the cosmos. The evidence is overwhelming. The discovery of dark energy didn't just change our understanding of the past, it altered our vision of the future. The two possible endings we had imagined, the Big Crunch or the Big Freeze, were based on gravity. But the accelerating universe presents a new, more lonely and desolate fate. If dark energy is the cosmological constant, a constant energy inherent to space, then our universe is heading for a future often called the Big Freeze. As the expansion accelerates, a cosmic horizon forms around us. Galaxies on the other side of this horizon are carried away so fast that their light can no longer reach us. Over the coming billions of years, this process will continue. One by one, distant galaxies will wink out. The night sky will grow darker. In about 100 billion years, every single galaxy outside of our own local group will have vanished from view. Our descendants, if any exist, might look out into an almost completely empty sky and conclude, quite logically, that theirs is the only galaxy in the universe. The timeline then stretches into the truly astronomical. Star formation will cease. The stars will slowly burn out. The universe will become a realm of stellar remnants, black holes, neutron stars, and cold, dead white dwarfs. Given almost unimaginable timescales, even these will decay. The universe will become a vast, cold, dark, and almost perfectly empty void. It will be a universe without structure, without heat, without life, and without end. A quiet, eternal emptiness. But there is another, more violent possibility. What if dark energy is not constant? Some theories propose a form of phantom energy, where the density of dark energy actually increases as the universe expands. If this is the case, the universe is destined for a more spectacular end, the Big Rip. In this scenario, the repulsive force would grow stronger and stronger. A few 100 million years before the end, it would unbind galaxy clusters. Then, galaxies themselves would be torn apart. In the final months, planetary systems would be ripped apart. In the last few minutes, stars and planets would disintegrate. In the final fractions of a second, atoms themselves would be ripped apart. The fabric of space-time would be torn asunder. The universe would end not in a cold whimper, but a violent scream. Right now, our best data suggests the Big Freeze is our most likely fate. The measured properties of dark energy are very consistent with a cosmological constant. But the measurements are not yet precise enough to completely rule out the Big Rip. Our cosmic destiny still hangs in the balance. We have a name for our ghost, dark energy. We have evidence for its existence. We have a prime suspect, the energy of the vacuum. And yet, we are left with what is arguably the greatest mystery in all of science. The problem is this. We can try to calculate how much vacuum energy there should be using quantum field theory. When we do this, we get a number. An absurdly, catastrophically large number. The value predicted by our best theories is about 10 to the power of 120 times larger than the value we actually observe. This is the single greatest disagreement between theory and observation in the history of physics. If the vacuum energy were as large as theory predicts, the universe would have ripped itself apart in the first fraction of a second. Stars and galaxies would never have formed. We would not be here. This is the cosmological constant problem, and it tells us that there is something fundamental we are missing. Why is the observed value of dark energy so ridiculously small compared to the theoretical prediction? No one knows, and the mystery only deepens. As if this weren't enough, recent evidence has begun to hint at an even stranger possibility. For 2 decades, our leading model has assumed dark energy is constant. But is it? The latest results from the Dark Energy Spectroscopic Instrument, (DESI), announced in recent years, have provided a stunning new twist. By creating the largest 3D map of the universe ever made, scientists found hints that dark energy may not be constant at all. The data suggests its influence might be evolving, perhaps even weakening over time. This is not yet a definitive discovery, the statistical evidence is still just below the gold standard. But it is the strongest sign yet of a crack in our standard model. If dark energy changes over time, then it cannot be Einstein's simple cosmological constant. It must be something else entirely. While some data from projects like the Dark Energy Survey strongly confirm the constant model, Dacey sees these tantalizing signs that the story is more complicated. We are at a tipping point. We find ourselves in a strange and thrilling moment. We set out to take a simple measurement, and instead, we stumbled upon an invisible force that dominates our universe and dictates its fate. We have learned that over 2/3 of our cosmos is made of an energy whose existence defies our best theories. And now, just as we were getting used to this bizarre new reality, new clues suggest that even this story might be changing. But we are not standing still. A new generation of magnificent observatories is coming online. The Euclid Space Telescope will map the shapes of billions of galaxies to track the history of dark energy. The Vera C. Rubin Observatory will create a dynamic movie of the southern sky. And NASA's Nancy Grace Roman Space Telescope will perform a cosmic census of millions of supernovae. These incredible machines are our response to the mystery. They are our tools to see if dark energy is a constant or if it is changing. To figure out if our fate is a freeze, a rip, or something else entirely. The discovery of the accelerating universe was a lesson in cosmic humility. It taught us that the more we learn, the more we realize how little we know. We are living in a universe that is not only stranger than we imagine, but stranger than we can imagine. And the quest to understand the invisible force tearing it all apart is the greatest scientific adventure of our time. If you want to continue exploring the frontiers of science and the deepest questions about our universe, make sure you're subscribed. For another dive into the cosmic unknown, check out our video on dark matter, the other great mystery that dominates the cosmos. Thank you for joining us on this journey. And as always, keep looking up. Physics 120-digit error that rewrites reality. Imagine looking out into the space between stars. It appears to be a perfect void, an expanse of absolute nothing. Yet our most trusted theories in physics tell us that this emptiness is not empty at all. It holds a vast, hidden energy. When we try to calculate how much energy there should be, the result is a number so large it suggests the universe should have torn itself apart in the first moments of its existence. This is the story of a disagreement. Not a small one, but perhaps the most significant disagreement between theory and observation ever encountered in science. It concerns two of our most fundamental descriptions of the universe, one for the very large, and one for the very small. Where they meet, they produce a prediction about the energy of empty space that is wrong by 120 orders of magnitude. This discrepancy is known, quietly, as the vacuum catastrophe. The fact that we are here, that galaxies and stars exist, is evidence that something is deeply missing from our understanding. The source of this puzzle is the energy of the vacuum itself. What our theories predict and what our telescopes observe are profoundly different. This is more than just an error. It is a quiet, persistent problem that has guided the course of fundamental physics for decades. Its solution promises to connect the quantum world to the fate of the entire universe. To understand how physics arrived at this point, our story has to begin over a century ago, with one of the most well-known figures in science, and what he would later call his single biggest blunder. An unwanted prediction. Our story begins in the early 20th century, a time when the world of physics was being reshaped. Albert Einstein had recently presented his general theory of relativity, a new way of understanding gravity. In his theory, gravity was not a force pulling objects together, but a consequence of spacetime itself being curved by mass and energy. Objects simply follow these curves in the fabric of reality. It was an elegant and revolutionary idea. Einstein's equations described the universe with remarkable precision, predicting the orbit of Mercury and the bending of starlight with an accuracy that older theories could not match. The confirmation of his theory during a 1919 solar eclipse made him a global figure. But there was a problem. When Einstein applied his equations to the entire universe, they suggested something that went against the prevailing view of his time. They predicted that the universe could not be still. It had to be either expanding or contracting. In the early 1900s, the consensus was that the universe was static and eternal. The idea of a dynamic, evolving cosmos was not yet part of the scientific vocabulary. Faced with this conflict between his theory and the accepted view, Einstein felt his equations might be incomplete. He introduced a new term, which he called the cosmological constant. Represented by the Greek letter lambda, this term represented an intrinsic energy of space itself. A kind of gentle, constant push that would counteract the pull of gravity. He chose its value carefully to balance the inward pull of all the matter in the universe, resulting in the static cosmos that he and other scientists believed in. Just a decade later, in 1929, the astronomer Edwin Hubble, using the powerful telescope at Mount Wilson Observatory, found something unexpected. The light from distant galaxies was stretched, shifted toward the red end of the spectrum. This redshift was a sign that the galaxies were moving away from us. More than that, the farther away a galaxy was, the faster it appeared to be receding. This was the signature of space itself expanding, carrying the galaxies along with it. The universe was not static. Einstein's original equations had been right all along. They had predicted the expanding universe before it was discovered. His added term, the cosmological constant, was not needed. After visiting Hubble and seeing the evidence, Einstein reportedly referred to the introduction of the constant as his biggest blunder. He had seen the truth in his equations and set it aside because of his own preconceptions. For many years, the cosmological constant was seen as a historical footnote, a lesson about forcing a theory to fit an idea. The case seemed closed. But in science, ideas can sometimes return in unexpected ways. Einstein's blunder was about to be re-examined, not because of the very large, but because of the very small. And this is where the story takes a quiet, but dramatic, turn. The energy of nothing. To understand where the enormous prediction for the universe's energy comes from, we have to leave the world of galaxies and curved space-time, and journey into the quiet, counterintuitive realm of quantum mechanics. It is a world where our everyday sense of nothing begins to change. One of the cornerstones of this world is the uncertainty principle. It states that there is a fundamental limit to how precisely you can know certain pairs of properties at the same time. For instance, the more precisely you know a particle's position, the less precisely you can know its momentum. This principle also applies to energy and time. The uncertainty principle implies that you cannot know the exact energy of a system for an infinitely small moment. There is always a fundamental fuzziness. This means that energy can be borrowed from the vacuum, from empty space, as long as it is returned in an incredibly short amount of time. This suggests that empty space is not truly empty. It is a field of quiet, constant activity. Out of the vacuum, pairs of virtual particles and their antimatter counterparts can briefly come into existence before disappearing again. An electron and a positron, a quark and an antiquark, materializing and dematerializing in a constant, high-energy exchange. The vacuum is alive with this subtle dance. This inherent energy that exists even in a perfect vacuum is called zero-point energy. Every quantum field that fills the universe, the electromagnetic field, the Higgs field, and others, has this baseline energy. It is the lowest possible energy state, but that state is not zero. If it were, the field would have a definite value and a definite rate of change, which would violate the uncertainty principle. So every point in space hums with this fundamental energy. This brings us to our most successful description of this world, quantum field theory, or QFT. Its predictions have been confirmed with astonishing precision. So, what happens when we use this theory to calculate the energy of the vacuum? The process involves adding up the zero-point energy of all the quantum fields we know. We sum the energy contribution from all possible fluctuations, down to the smallest possible scale where our current theories still apply, known as the Planck length. When physicists perform this calculation, the number that emerges is difficult to comprehend. It is an energy density of roughly 10 to the power of 113 joules per cubic meter. It is one of the largest numbers to ever appear in a physical calculation. And here is where our two stories meet. The cosmological constant, lambda, which Einstein introduced to represent an intrinsic energy density of space, now has a theoretical origin. The zero-point energy predicted by quantum mechanics should manifest itself on a cosmological scale as the cosmological constant. The theory of the very small has made a prediction about the behavior of the very large. If this prediction were true, the repulsive force of this energy would be so immense that it would overwhelm gravity on all scales. The expansion of the universe would have been so rapid that the fabric of space would have been torn apart in the first fraction of a second. No structures could have formed, no atoms, stars, or galaxies. But we are here. We exist. We see a universe filled with structure. This simple fact proves that the energy of the vacuum cannot be that large. Our theoretical calculation must be wrong. And not by a small amount. This is where the story takes its final, mind-bending turn, with a discovery that would reveal the true scale of this quiet catastrophe. We are exploring one of the deepest puzzles in modern physics, a story that connects the beginning of the universe to its eventual fate. If this kind of calm exploration into the world of science helps you unwind, consider liking the video and subscribing to the channel. We have more ground to cover, including the discovery that revealed the true nature of this problem. Now, let's return to the mystery. The blunder that was right. For much of the 20th century, the story of cosmology was one of a slowing expansion. The universe was born in the Big Bang and has been expanding and cooling ever since. Gravity, the collective pull of all the matter in the cosmos, was thought to be acting as a brake. The main question was whether there was enough matter to eventually halt the expansion and cause a big crunch, or if the universe would expand forever into a cold, dark, big freeze. To answer this, astronomers needed to measure how the expansion rate had changed over time. In cosmology, looking far away is looking into the past. By comparing the expansion rate of the nearby universe with that of the distant, past universe, they could see how much gravity had been slowing things down. The key was finding a standard candle, an object of known brightness that could be seen across cosmic distances. In the 1990s, two independent teams decided to use a particular kind of exploding star, a type Ia supernova, for this purpose. These supernovae are useful because they are thought to all explode with roughly the same peak brightness, making them reliable cosmic distance markers. Two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, began to search the sky for these distant explosions. Their goal was to measure the slowing of the universe's expansion. As they collected their data, they found that the most distant supernovae were dimmer than they should have been. This suggested they were farther away than the models of a decelerating universe predicted. If they were farther away, it meant the expansion of the universe had not been slowing down. It had been speeding up. The teams checked for any possible source of error, but the result remained. The conclusion was inescapable. The expansion of the universe is accelerating. In 1998, the teams published their results. Some unknown influence, which physicists now call dark energy, was acting against gravity, pushing spacetime apart. This dark energy appeared to make up nearly 70% of the energy in the universe. The simplest candidate for what this dark energy could be was already there, waiting. It was Einstein's old cosmological constant. The supernova data seemed to require a constant, intrinsic energy density of space creating a repulsive force, just as Einstein had proposed. Suddenly, his blunder looked more like a prophecy. He had predicted the existence of this cosmic acceleration more than 80 years before it was discovered. So, physicists could now measure the actual value of this dark energy. From the supernova data and other observations, they calculated the actual energy density of the vacuum. The value they found was tiny. The observed energy density of space is about 10 to the power of -9 joules per cubic meter. It is a minuscule amount of energy, but on the scale of the cosmos, it is enough to drive its accelerating expansion. And now, we arrive at the heart of the problem. On one hand, we have the theoretical prediction from quantum field theory for the vacuum's energy density, 10 to the power of 113 joules per cubic meter. On the other, we have the observed value from cosmology, 10 to the power of -9 joules per cubic meter. The difference between these two numbers is approximately 120 orders of magnitude. It is the single greatest mismatch between theory and observation in the history of science. It means our understanding of the energy of nothing is incomplete on a scale that is difficult to express. The problem is one of extreme fine-tuning. For the universe to exist as it is, the enormous positive energy predicted by quantum theory must be cancelled by some other, unknown effect with almost perfect precision. Imagine two enormous numbers, which are equal and opposite to such a degree that they cancel each other out for the first 121 decimal places, leaving only a tiny remainder. What physical principle could be responsible for such an impossibly precise cancellation? This is the question that defines the vacuum catastrophe. It signals that something is profoundly missing in our two great theories, general relativity and quantum field theory, or in how we connect them. The search for a solution has become one of the most important goals in all of physics. Exploring the possibilities. Faced with this profound disagreement, physicists are looking for a mechanism that could explain this 120-digit error. The investigation has led down some of the most interesting and speculative paths in theoretical physics. **1. A perfect cancellation. One of the most elegant ideas was a theory called supersymmetry. It proposes a new symmetry in nature connecting the two fundamental types of particles. Fermions, the particles of matter, and bosons, the particles that carry forces. In a supersymmetric world, every known particle would have a hypothetical superpartner of the other type. This is helpful because it turns out that fermions and bosons contribute to the vacuum energy with opposite signs. If supersymmetry were a perfect, unbroken symmetry, the contribution from each particle would be perfectly cancelled by its superpartner. The resulting vacuum energy would be exactly zero. This is much closer to the tiny observed value. The problem is, we have never seen any of these superpartner particles. If they existed with the same mass as their partners, we would have found them in our particle accelerators. This means that if supersymmetry exists, it must be broken, the superpartners must be much heavier. But as soon as the symmetry is broken, the perfect cancellation is lost, and a large vacuum energy reappears. **2. The cosmic lottery. If a law cannot be found to explain the small value of the vacuum energy, perhaps the answer is that we are simply in a place where it happens to be small. This is the core of the anthropic principle, an idea that grew out of string theory. String theory suggests the possibility of a vast landscape of perhaps 10 to the power of 500 possible universes, each with its own physical laws. In this multiverse, every possible value for the vacuum energy would exist somewhere. The vast majority of these universes would have a large vacuum energy and could not support life. Only in the tiny fraction of universes where, by chance, the vacuum energy is very close to zero, would the conditions be right for observers like us to evolve? The argument is that we observe a small cosmological constant because if it were large, we would not be here to observe it. To many, this feels less like a physical explanation and more like a statistical one. It is a deeply debated topic, in part because it may be impossible to test. ****3. A flaw in the law. What if the problem is not with the energy itself, but with how it interacts with gravity? Our calculations are based on Einstein's general relativity. But what if the enormous energy of the quantum vacuum does not gravitate in the same way as matter and radiation? This leads to another path: modifying the laws of gravity. Perhaps general relativity is an approximation that works well for planets and stars, but needs to be adjusted on the scale of the entire cosmos. These ideas are still developing, and they face a major challenge. General relativity has passed every experimental test thrown at it. Any new theory must also reproduce all of its known successes. ***4. A dynamic value. A final possibility challenges a core assumption that the cosmological constant is actually constant. What if the energy density of the vacuum changes over cosmic time, evolving as the universe expands? This idea is appealing because it connects the value of the vacuum energy to the dynamics of the cosmos itself, rather than it being a fixed, arbitrary number. It suggests a deeper feedback between the quantum vacuum and the geometry of spacetime. These models are still being tested against our improving cosmological data. Each of these possibilities represents a profound shift in our standard picture of physics. As of today, the case remains open. The universe in the balance. We began with what looks like an accounting error and have arrived at one of the deepest mysteries in science. The vacuum catastrophe is not just a numerical problem. It is a chasm in our understanding of existence, where our two greatest theories failed to connect. Quantum mechanics insists that empty space must hold a vast energy. Cosmology shows us a universe driven by an amount of energy so small it appears to be balanced on a knife's edge. The problem is not just that the number is finely tuned, it is that the existence of a stable universe at all seems to depend on this tuning. For decades, we have tried to solve this puzzle. We have explored new symmetries, imagined other universes, and questioned the laws of gravity. Yet the mystery endures, a quiet reminder of how much we still have to learn. But a crisis in science is also an opportunity. A great failure is a great clue. The vacuum catastrophe is a signpost, pointing toward a new, deeper physics we have not yet imagined. Its solution may require us to finally unite quantum mechanics and gravity into a single theory. It may force us to reconsider our place in a multiverse. Or it may reveal a new principle of nature as fundamental as relativity or quantum mechanics itself. The fact that nothing has an energy is a core idea of modern physics. The fact that it has almost no energy is what allows for our existence. We live in that precarious balance, in the sliver of reality left over after two immense theoretical values have cancelled each other with unimaginable precision. The greatest mystery of the cosmos may not be in the hearts of distant stars, but in the quiet, empty space between them. The 120-digit error is a message, a whispered secret from the vacuum itself. And it is telling us that the greatest discoveries are still to come. Thank you for joining me on this journey to the edge of physics. The vacuum catastrophe is a puzzle that continues to challenge scientists around the world. What are your thoughts on these potential solutions? Feel free to share them in the comments below. If you enjoyed this deep dive into the mysteries of the cosmos, please consider giving this video a like and subscribing to the channel for more explorations of the biggest ideas in science. Scientists weighed the void and it changes everything. What if we could weigh a box of pure, empty space? For most of human history, the question itself would have seemed strange. We understood nothing as simply an absence, a void. But in one of the quiet, profound shifts in understanding that defined science, physicists found a way to measure the void, and they discovered it had weight. The weight they found is so small it appears insignificant, yet so fundamental that it seems to hold the story of the past, the present, and the eventual fate of our universe. This is not a story of analogy. The reality that nothing has substance is a deep part of why we are here, and it is the quiet force that will likely determine how everything ends. This is the story of how we learned that the vacuum of space is not empty, and how that realization slowly reshaped our model of reality itself. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether in a city, a forest, or somewhere quiet in between, feel free to share where you're watching or listening from. The crisis of a static universe. To understand why the weight of the void matters, we have to return to the beginning of modern cosmology, to a time when the universe was imagined as a simple, permanent, and quiet place. In the early 20th century, the prevailing view, held even by the greatest scientific minds, was that the cosmos was static. It had always existed, and it would always exist, an eternal stage on which the stars moved through their lives. At the center of this story is Albert Einstein. By 1917, he had offered the world his general theory of relativity, a new description of gravity not as a force, but as the curvature of spacetime itself. Mass and energy, he explained, tell spacetime how to bend, and in turn, the shape of spacetime tells mass and energy how to move. It was a beautiful, elegant theory, one that correctly predicted the orbit of Mercury where Newton's description had fallen short. But when Einstein applied his own equations to the universe as a whole, he arrived at a difficult conclusion. His mathematics suggested something that stood in direct opposition to the idea of a static universe. They showed that a universe filled with matter, with its vast, collective gravity, should be unstable. Gravity, being an attractive influence, should draw all things together. Over cosmic time, every galaxy and star should be pulled closer and closer, destined to collapse in on themselves. Under his own rules, a static universe was not possible. It should have collapsed long ago. This was a quiet crisis. Faced with a conflict between his theory and the accepted model of the cosmos, Einstein chose a path of preservation. He concluded his equations might be incomplete. To correct them, he introduced a new term, what he called the cosmological constant, represented by the Greek letter lambda. This constant would represent a kind of inherent energy in space itself, an outward pressure that could perfectly balance the inward pull of gravity. It would hold the universe still. He was not satisfied with the solution. It felt like a mathematical invention without physical justification. But it seemed necessary. For more than a decade, the cosmological constant remained in his equations, a placeholder for cosmic stability. But then, understanding changed. In 1929, the American astronomer Edwin Hubble, using the most powerful telescope of his era, made a landmark observation. While measuring the light from distant galaxies, he noticed something consistent. The light was stretched, shifted toward the red end of the spectrum. This redshift was a clear sign of the Doppler effect, the same phenomenon that causes an ambulance siren to sound lower in pitch as it moves away. The conclusion was difficult to escape. These distant galaxies were not stationary. They were all moving away from us. And the farther a galaxy was, the faster it was receding. The universe was not static at all, it was expanding. The discovery of an expanding universe removed the foundation for Einstein's correction. There was no need for a force to counteract gravitational collapse, because the universe was not collapsing. It was growing, carried outward by the momentum of some ancient, powerful beginning. Einstein, recognizing this, abandoned his corrective term, famously referring to the cosmological constant as his biggest blunder. He had been so focused on making reality fit the assumptions of his time that he had missed the chance to predict the expansion himself, a prediction that was already present in his original equations. And so, the cosmological constant was set aside, viewed as a relic from a mistaken idea. Or so it seemed. The quantum revolution and the nature of nothing. As cosmology was coming to terms with the grand scale of the universe, another revolution was taking shape in the world of physics, one that would change our understanding of the very small. This was the beginning of quantum mechanics, and it would eventually bring Einstein's blunder back into the conversation. The classical picture of the universe is of a world made of tiny, solid particles moving through a vast, empty void. But quantum mechanics revealed this to be a simple approximation of a much stranger reality, one described by quantum field theory, or QFT. QFT is the language of modern physics, and its central idea is a radical one. The most fundamental things in the universe are not particles. They are fields. Imagine an invisible, silent medium that permeates every point in space and time. This is a field. A ripple or a localized vibration in that medium is what we perceive as a particle. An electron is not a small ball, it is an excitation of the electron field. A photon of light is a ripple in the electromagnetic field. Every fundamental particle we know has its own corresponding field, extending throughout the entire universe. This screen, the planet Earth, the distant stars, all are intricate, complex patterns of interacting ripples in these fundamental quantum fields. The world is not made of objects, it is made of excitations. It is a profound shift in perspective. Reality is not a collection of things inside an empty container. The container itself has properties that give rise to everything within it. So, what remains in a perfect vacuum if you remove all the particles, all the ripples? The fields themselves. Even in the deepest void, the electron field, the quark fields, and all the others are still present. They are in their lowest possible energy state, their ground state, like a perfectly calm ocean. But this is where the quiet strangeness of the quantum world appears, through one of its foundational rules, the Heisenberg Uncertainty Principle. The principle states that certain pairs of properties in a quantum system can never be known with perfect precision at the same time. This principle also applies to the energy of a quantum field. One cannot say that a region of a field has exactly zero energy, because that would be a precise measurement. Instead, the field must always fluctuate, even in its ground state. At every point in space, the fields are constantly vibrating with a minimum, non-zero amount of energy. This irreducible, baseline energy of the vacuum is called zero-point energy. This quantum fluctuation is not just a theoretical idea. It has a real presence. The fields in the vacuum constantly produce fleeting pairs of virtual particles and virtual antiparticles that emerge from the field, exist for an immeasurably short time, and then annihilate. This constant shimmer of transient particles is sometimes called quantum foam. Empty space, according to quantum field theory, is not empty at all. It is a quiet, energetic medium of potential. For a long time, this vacuum energy was mostly set aside. In many calculations, only changes in energy are important, not the baseline amount. So physicists would recenter their measurements, setting this background energy to zero for convenience. It was seen as a curious feature of the quantum world, an ocean of energy that seemed to have no consequence on our reality. But they had not forgotten Einstein. They had not forgotten that in the world of general relativity, all energy has a gravitational effect. And the energy of the void, this zero-point energy, was about to gently converge with the expansion of the universe. Weighing the void. This brings us to the center of our story, the moment where these two great descriptions of reality, general relativity and quantum field theory, meet. The question was simple, but its implications were vast. If the vacuum is filled with this zero-point energy, does it have weight? According to general relativity, the answer is yes. The theory is clear that it is not just mass that bends space-time and creates gravity. Energy does as well, linked by the equation E equals mc squared. Any form of energy will have a gravitational consequence. This vacuum energy should be no different. Its energy density should behave just like Einstein's old cosmological constant. It would be a property of space itself, a source of gentle, persistent repulsion. Unlike matter, which thins out as space expands, this energy is part of the fabric of spacetime. As the universe expands and more space is created, the total amount of vacuum energy increases. More space means more vacuum energy, which in turn causes space to expand faster. It creates a quiet feedback loop, an accelerating expansion. For decades after Hubble's discovery, this idea remained a theoretical curiosity. The universe's expansion was believed to be slowing down, restrained by the gravitational pull of all the matter within it. Cosmologists worked to measure how much the expansion was slowing, hoping to determine the universe's ultimate fate. If there was enough matter, its gravity would eventually stop the expansion and pull everything back into a big crunch. If there was not enough, the universe would expand forever, growing colder and darker in a big freeze. The work was to take a census of the cosmos and find the answer. This is where the story shifts, in the late 1990s, to two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team. Both were using an elegant method to measure the history of cosmic expansion with new precision. Their tool was a specific type of exploding star, the type Ia supernova. These explosions are special. They happen when a white dwarf star pulls too much matter from a companion, surpassing a critical mass. When this occurs, it sets off a thermonuclear explosion that is, in every case, fundamentally the same. Because the explosion is always triggered by the same amount of mass, the intrinsic brightness of a type Ia supernova is always the same. They're standard candles. If you know the absolute brightness of a light, you can calculate its distance by measuring how dim it appears. Type Ia supernovae are so bright they can briefly outshine their entire host galaxy, making them visible across billions of light years. By finding these distant explosions and measuring their apparent brightness, the teams could calculate their distance. They could also measure their redshift, which revealed how fast they were moving away. By comparing distance and redshift for supernovae at different points in the universe's past, they could create a map of cosmic expansion over time. Both teams expected to find that the expansion was slowing. The only question was by how much. But as the data was collected, it began to show something that did not fit the expected model. The most distant supernovae were dimmer than they should have been. This meant they were farther away than their redshift suggested. The implication was that in the time it took their light to reach us, the universe had expanded more than expected. The expansion wasn't slowing down. It was speeding up. The discovery, announced in 1998, quietly reordered the field of cosmology. It went against the prevailing model of a universe governed by gravity's braking force. The universe was accelerating. Gravity was not the only force in the cosmic tug-of-war. Some other mysterious influence, a dark energy, was pushing the universe apart. For this discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees would share the 2011 Nobel Prize in Physics. And suddenly, Einstein's biggest blunder no longer looked like a blunder. It looked like a prediction. The cosmological constant, the idea of an intrinsic energy of space itself, was the most natural explanation for this cosmic acceleration. The astronomers had, in a sense, weighed the void. By measuring the rate of acceleration, they could calculate the energy density needed to cause it. The result was incredibly small, around 5.96 times 10 to the minus 27 kilograms for every cubic meter of space. This is a tiny amount of mass energy. But this tiny number is a property of every cubic meter of space. When multiplied by the volume of the observable universe, the total amount of this dark energy is enormous. The data suggests that this energy of the void makes up roughly 68% of the total mass energy content of the universe. Think about that for a moment. All the stars, galaxies, gas, and dust, all the familiar matter, makes up less than 5% of the universe. The rest, the overwhelming majority, is dark matter and this energy of nothing. We live in a universe dominated by the weight of empty space. The discovery was a triumph, but in solving one mystery, it created another, one so profound it has been called the most significant puzzle in physics. The cosmological constant problem. The moment scientists had a measured value for the energy of the vacuum, they could compare it to what theory predicted. On one side was the astronomer's measurement, taken from the gentle, observed acceleration of the cosmos, a tiny, positive number. On the other was the physicist's calculation, derived from the energetic, fluctuating world of quantum field theory. And when they placed the two numbers side by side, the result was not just different. The disagreement was on a scale that is difficult to comprehend. The theoretical calculation goes like this. Quantum field theory suggests that every quantum field contributes zero-point energy to the vacuum. To estimate the total vacuum energy, you must add up the contributions from all the fields and all their possible fluctuations, down to the smallest possible scales. When you do this calculation, the number you get for the expected energy of the vacuum is enormous. It is about 10 to the power of 121 times larger than the value we actually observe. This is not a small error. It is the largest discrepancy between theory and experiment in the history of science. This quiet mismatch is known as the cosmological constant problem. If the vacuum energy were as large as the theory suggests, the universe would be unrecognizable. The repulsive force would have been so immense it would have torn space apart fractions of a second after the Big Bang. Atoms would never have formed. Stars and galaxies would have been impossible. So we are left with a deep and unsettling question. Observation tells us there is a small amount of vacuum energy, just enough to gently accelerate the universe's expansion. Theory tells us there should be a monstrous amount. Why is the actual value so small? And if it isn't zero, why is it this particular value, so exquisitely fine-tuned to allow for a universe like ours? It seems that some unknown process cancels out the enormous energy predicted by quantum theory, canceling it almost perfectly, but not completely. Imagine subtracting two numbers, each with more than 100 digits. They cancel each other out in every digit except for the very last one, leaving a tiny remainder. That remainder appears to be the universe we inhabit. This problem suggests that our two most successful theories of reality, general relativity and quantum field theory, do not fit together correctly. Something is missing from our understanding of how gravity and the quantum world interact. The search for an answer has led to some of the most subtle and complex ideas in science. One early hope was a principle called supersymmetry, which proposes that every known particle has a superpartner with different properties. It turns out these partner particles would contribute to the vacuum energy with an opposite sign, potentially canceling each other out. The problem is, we have not found any of these superpartners. If they exist, the symmetry must be broken, meaning the cancellation would not be perfect. Another, more philosophical idea is the anthropic principle, often paired with the concept of a multiverse. This suggests there may be many universes, each with its own value for the cosmological constant. In most, the value is huge, and they either collapse instantly or expand too fast for any structure to form. We simply find ourselves in one of the rare universes where the value happened to be small enough to allow for stars, galaxies, and observers to emerge. To many physicists, this feels less like an explanation and more like giving up on finding a fundamental reason. Other ideas propose that our understanding of gravity itself is incomplete, or that the cosmological constant is not constant at all, but a dynamic field that has changed over time. The problem remains unsolved. It is a quiet reminder that there are still deep gaps in our knowledge. And yet, even as we struggle with the why, there is undeniable proof that the energy of the void is real, and it comes not from the cosmos, but from a delicate experiment on Earth. The proof: a force from nothing. While astronomers looked to the sky, the Dutch physicist Hendrik Casimir had predicted a way to detect vacuum energy in a laboratory as far back as 1948. His idea was a beautifully simple thought experiment, based on the core ideas of quantum field theory. As we've discussed, the vacuum is filled with fluctuating fields of all possible wavelengths. Casimir reasoned that if you place two uncharged metal plates extremely close to each other, you alter the vacuum between them. The space between the plates acts as a resonant cavity. Only virtual photons whose wavelengths fit neatly into the gap can exist there. Longer wavelengths are excluded. Outside the plates, however, there are no such restrictions. This means there are more quantum fluctuations on the outside of the plates than on the inside. This imbalance creates a pressure difference. The greater pressure from the vacuum outside gently pushes the plates together. This tiny, attractive force, born from the structured energy of the void, is the Casimir effect. For decades, this was only a theoretical prediction. But in 1996, Stephen Lamoureux and his team performed a definitive measurement of the effect, which was reported in 1997. Using a highly sensitive instrument, they detected the minuscule attraction between two surfaces. The results matched Casimir's prediction. Since then, the experiment has been repeated with increasing precision, confirming the reality of the Casimir force. It is tangible, experimental proof that the vacuum is not empty. The quantum foam is real. You can measure the force of nothing. It is a direct bridge between the abstract world of quantum theory and the mechanical world of pushes and pulls. This leads to a natural question. If the vacuum is filled with this energy, can we use it? Could we build a machine that taps into the zero-point energy of spacetime? The answer, it seems, is no. The laws of thermodynamics remain undefeated. You can only extract energy when something moves from a higher energy state to a lower one. Zero-point energy is, by definition, the lowest possible energy state of the vacuum. There is no lower state to fall to. So, while the Casimir effect does not offer a solution to our energy needs, its importance is hard to overstate. It is a quiet confirmation, a tangible echo, showing that the same mysterious energy that drives the acceleration of the universe on the largest scales also operates in a laboratory on Earth. A universe built from nothing. So, where does this leave our understanding? We've journeyed from a static universe to an expanding one, from the discovery of cosmic acceleration to the deep puzzle of the cosmological constant. We have seen how the void, once seen as a passive backdrop, is in fact an energetic, dynamic medium. To live in a universe built from this structured emptiness forces us to re-evaluate our most basic ideas about reality. First, the concept of solid matter becomes an illusion. The particles that make up atoms, the electrons, the quarks, are just localized vibrations in their respective fields. An atom is not so much a thing as it is a stable dance of field excitations. What we perceive as solid is just the powerful interaction of these fields. The universe is not empty space containing a few bits of substance. The universe is the fields, and the substance is just the visible froth on their surface. Second, the weight of the void appears to dictate the timeline of the cosmos. In the early universe, matter was densely packed, and the attractive force of gravity was dominant. For the first 9 billion years, gravity was slowing the expansion that began with the Big Bang. But as the universe expanded, matter thinned out, and gravity's influence weakened. The vacuum energy, however, remained constant in its density. As more space was created, the total repulsive power of the vacuum grew. About 5 billion years ago, a tipping point was reached. The outward push of dark energy overtook the inward pull of gravity. This is the era we live in now, an age of accelerating expansion. And this acceleration will shape the future. As it continues, distant galaxies will be pushed away from us faster and faster, eventually receding at speeds greater than the speed of light. Their light will no longer be able to reach us. They will vanish from our sky. The cosmos will become a far emptier, more isolated place. The final chapter of the universe seems not to be a fiery collapse, but a cold, quiet, and accelerating expansion into darkness, driven by the energy of the void itself. This story is a clear example of the scientific process. It began with a theoretical problem, leading to a correction that was later discarded. Decades later, an unexpected observation forced a new model of the cosmos. This observation brought back the old correction, turning it from a blunder into a profound discovery. But this discovery, in turn, created an even deeper conflict with our understanding of the quantum world, a mystery that now points us toward a more complete theory of physics. It is a journey from a puzzle, to a solution, to an even greater puzzle. For those who wish to explore more about the quantum fields that make up our reality, you might find our video on the real-life matrix. Is the universe made of fields? Interesting? The link is in the description. We began with a simple question. What is the weight of nothing? We found that the answer is not zero. The vacuum of space-time has a tiny, inherent energy, a weight that is pushing our universe apart. This energy will likely dictate the ultimate fate of all things. This discovery requires a shift in our perception. We are used to thinking of the world in terms of objects and the empty space between them. Physics now suggests this might be backwards. The empty space is the fundamental entity, an energetic ocean of quantum fields. The objects we see are merely disturbances in this ocean, temporary patterns in a landscape of structured nothingness. The great mystery that remains, the cosmological constant problem, is a clue. This failure of our current theories is not an end. It is a signpost, pointing the way toward a deeper understanding, perhaps to a new theory that will finally unite gravity with the quantum world. So the next time you look up at the night sky, at the vast, dark emptiness between the stars, remember what you are looking at. You are not seeing an absence. You are seeing the most dominant substance in the universe. An invisible presence that fills all of space, that was part of the conditions that allowed for our existence, and that is slowly, patiently, shaping the end of the cosmos. You are looking at the weight of the void, and its presence reorders our understanding of everything.